Nobody lied to you about Mars. They just didn't tell you all of it. The part they left out isn't speculation, and what it says about your body on Mars is deeply uncomfortable. So ask yourself this: how much of the truth are you actually ready to hear, and why you wouldn't survive 1 year there? If that kind of deep, honest look at the universe is what you're after, make sure to give this video a like. Now let's get started. Forget the dusty landscape you've seen in 100 photos, because the most dangerous thing about Mars is something you cannot see. It has no color, it makes no sound, and on Earth, you have never once had to think about it, because our planet has spent 4.5 billion years building an invisible shield to protect you from it. That shield is Earth's magnetic field, and Mars lost its version of that shield somewhere between 3.7 and 4 billion years ago. Earth's magnetic field is generated by the movement of liquid iron and nickel churning inside our planet's outer core. That churning creates electric currents, and those currents generate a magnetic bubble. Scientists call it the magnetosphere, that stretches tens of thousands of kilometers out into space in every direction. It deflects the solar wind. It redirects the most dangerous particles that the sun hurls at us every single second of every single day. Without it, life on Earth as we know it simply would not exist. Mars once had something similar. The MAVEN mission, that's the Mars atmosphere and volatile evolution spacecraft that NASA put into Martian orbit in 2014, gave us some of the clearest evidence yet of what happened. Mars had a global magnetic field billions of years ago. We can still see the traces of it fossilized in ancient Martian rocks in the southern highlands. But the planet's interior cooled, the churning stopped, the magnetic field collapsed, and when it did, the solar wind began stripping away the Martian atmosphere, molecule by molecule, across hundreds of millions of years. What's left of that atmosphere today is almost nothing. The atmospheric pressure on the surface of Mars is about 600 pascals. Earth's is around 101,300 pascals. That means the Martian atmosphere is less than 1% as thick as ours. Standing on the surface of Mars without a pressurized suit would be like standing in a near-perfect vacuum. Your blood would begin to boil, not from heat, but because the pressure is so low that the boiling point of water drops below body temperature. You would lose consciousness within seconds. You would be dead within minutes. But even if you had a suit, even if you had the best pressurized suit ever engineered, the radiation would still be getting through. Here's where the physics becomes deeply personal. Radiation on Mars doesn't come from just one source. It comes from two. The first is galactic cosmic rays, high-energy particles that come from outside our solar system, accelerated by supernovae and other violent events across the galaxy. These particles travel at significant fractions of the speed of light and carry extraordinary amounts of energy. On Earth, our magnetic field and our thick atmosphere stop most of them before they ever reach the ground. On Mars, with almost no atmosphere and no magnetic field, they rain down constantly. The second source is our own sun. The sun regularly releases enormous bursts of energetic particles called solar particle events during periods of high activity. On Earth, these events occasionally disrupt satellites and power grids, but they don't reach you standing on the surface. On Mars, a powerful solar particle event can dramatically spike the radiation level on the surface within hours. In September of 2017, the Sun released one of the most powerful solar flares ever recorded, an X9.3 class flare. NASA's Mars Science Laboratory team ran the numbers on what that event would have meant for an unshielded astronaut on the Martian surface. The spike in surface radiation was significant enough to be detected clearly by RAD, even through what thin protection the Martian atmosphere provides. A major solar particle event of sufficient magnitude could deliver what scientists classify as an acute radiation syndrome dose, the kind that causes nausea, vomiting, and cellular damage within hours, depending on the shelter available. Now, to be precise, a single event like that would likely not kill a properly suited astronaut outright. Modern mission planning does account for solar particle event shelters. But here's the thing, you don't get to predict when those events happen. You don't get 2 weeks' notice. Sometimes you get minutes. And on a planet where your entire life support infrastructure is sitting on the surface, in thin atmosphere, with no magnetosphere above you, the margin for error is essentially zero. And the chronic exposure is just as serious, even if it's slower. Let's go back to that number. 0.64 millisieverts per day over the course of a full Martian year, which is about 687 Earth days, nearly 2 of our years. That adds up to somewhere around 440 millisieverts of radiation just from baseline surface exposure. That's not counting any major solar particle events. That's just the background noise. To put that in context, a full-body CT scan, the kind a doctor might use to check for cancer, delivers about 10 millisieverts in a single session. The annual occupational limit for radiation workers in most countries is 20 millisieverts per year. The career limit NASA sets for its astronauts to stay below a 3% increased risk of fatal cancer used to be capped at 1,000 millisieverts, though that limit has been updated and is now calculated based on individual age and sex-specific risk factors under a framework updated in recent years. What this means is that a single Martian year on the surface would bring you to a significant fraction of a lifetime radiation budget. And every day you stay past, that is compounding the biological damage to your DNA, damage to the cells lining your gut, damage to your bone marrow, damage to the tissues of your central nervous system. A 2013 study published in the journal PLOS One, based on data from the Curiosity rover's transit to Mars and its early surface measurements, estimated that a round-trip Mars mission of approximately 530 days on the surface, plus the transit time, would expose astronauts to roughly 1.01 sieverts of total radiation. That correlates to roughly a 5% increase in lifetime cancer risk from radiation alone. That's not a death sentence on its own, but combine it with everything else. Mars is waiting for you, and the picture becomes far darker, and we haven't even talked about the soil yet, or the temperature, or the dust. Actually, I made a video not long ago where we explore why the first humans on Mars will never return to Earth, and if the ideas in this video are landing for you, that one is going to hit even harder. It's on the card above. It takes everything we know about long-duration Mars missions and follows the logic all the way to its most uncomfortable conclusion. The link is in the description and pinned on the comments. You might imagine that the biggest threat on Mars is the sky, the radiation, the cold, the thin air, and those threats are absolutely real. But the ground beneath your feet is doing something quietly horrifying that took scientists decades to fully appreciate. In 2008, NASA's Phoenix lander, a stationary mission that touched down in the northern polar region of Mars, made a discovery that changed how we think about the entire planet's habitability. Its onboard instruments detected the presence of perchlorates in the Martian soil. Perchlorates are chlorine-containing compounds. Specifically, they're the salt form of perchloric acid, and they are toxic to human biology in ways that matter enormously for any long-term stay on Mars. On Earth, perchlorates exist in small amounts in certain arid environments, places like the Atacama Desert in Chile, which is often used as a Mars analog environment for that very reason. We know quite a bit about what perchlorates do to the human body because of cases of contaminated groundwater here on Earth. They disrupt the thyroid gland's ability to absorb iodine, and when the thyroid can't absorb iodine, it can't produce the hormones that regulate your metabolism, your heart rate, your body temperature, and your brain function. Long-term perchlorate exposure leads to hypothyroidism, a condition that causes fatigue, depression, weight gain, cognitive slowing, and in severe cases, serious cardiovascular and neurological damage. But on Mars, it gets worse. A 2017 study published in the journal Scientific Reports tested what happens when Martian perchlorate concentrations, which are between 50 and 100 times higher than the levels found in the most perchlorate-rich environments on Earth, are combined with the ultraviolet radiation that constantly bathes the Martian surface. The result was striking. Under UV irradiation, perchlorates become dramatically more bactericidal, meaning they become far more effective at destroying living cells. The study found that this combination could kill bacteria 3 times faster than UV alone. If that's what it does to bacteria, consider what it does to the delicate tissues of human skin, lungs, or eyes if the wrong particle of Martian dust ever finds its way past a seal, and Martian dust gets everywhere. That's not a metaphor. That's an engineering nightmare that every mission designer is currently wrestling with. The dust on Mars is not like beach sand. It's not like the dust bunnies under your furniture. It is an ultra-fine, chemically reactive powder made of particles so small that they behave almost like a liquid in certain conditions. They cling to surfaces with electrostatic charge. They work their way into seams, joints, and seals. They coat solar panels and reduce their efficiency dramatically, a reality that contributed to the eventual loss of the Opportunity rover, which went silent in 2018 after a global dust storm blocked the sunlight its solar panels needed to stay alive. Now imagine that dust is also laced with perchlorates. Imagine you're living in a habitat on Mars for months, and every time you come inside from an EVA, an extravehicular activity, a walk outside, you bring some of that dust with you. No matter how carefully you brush off your suit, no matter how good your airlock is, some of it gets through. Some of it always does, and then you breathe it. The implications for human pulmonary health on long-duration Mars missions are something researchers are actively and urgently studying, because we don't have a solution yet. We have proposals, we have ideas. We do not have a proven system that keeps perchlorate-laden Martian dust out of human lungs over the course of a year. We've covered radiation, atmosphere, and toxic soil, and we are only just getting started. Because the temperature on Mars, the psychological toll of isolation, what happens to your bones in reduced gravity, and the planet-wide dust storms that can last for months, those stories are coming. And some of them are going to surprise you. Here's what I want you to sit with before we get there. Everything we've talked about in this first section comes from real instruments, real missions, real data. The RAD detector on Curiosity, the Maven orbiter, the Phoenix lander. These are not simulations. These are not estimates pulled from thin air. This is Mars observed up close, telling us exactly what it thinks of our survival. And it is not optimistic, so stay with me, because the temperature section alone contains something that most people have completely wrong about Mars, and once you hear it, you'll never think about the planet the same way again. Most people, when they think about the temperature on Mars, picture something like Antarctica, brutal cold, sure, but the kind of cold that humans have actually survived in. The kind of cold that, with the right gear and the right preparation, can be endured. People winter over at Antarctic research stations all the time. They come back. They're okay. That comparison is not just wrong, it is dangerously wrong. And the reason it's wrong comes down to something that most popular science coverage of Mars completely glosses over. A detail that sounds almost too strange to be real until you understand the physics behind it. Let's set the scene properly. The average surface temperature on Mars is around -60 degrees Celsius. That already sounds extreme, but okay, extreme cold exists on Earth too. The lowest temperature ever recorded on our planet was -89.2 degrees Celsius at the Soviet Vostok station in Antarctica in 1983. So Mars is cold, but not incomprehensibly cold by Earth's absolute standards, right? Here's where it gets strange. On Earth, even at -89 degrees, the air around you, thin as it is at high altitude, still conducts heat. The atmosphere has enough density that it can physically transfer thermal energy. That's what cold feels like. The air is literally pulling heat out of your skin through conduction. The wind makes it worse through convection. You know this. You've felt wind chill on a cold winter day. On Mars, the atmosphere is so thin, less than 1% of Earth's, that it barely conducts heat at all. What that means is deeply counterintuitive. On Mars, if you were standing in direct sunlight near the equator on a clear afternoon, the surface temperature right beneath your boots could be as warm as 20 degrees Celsius. That's a comfortable spring day. But if you held your gloved hand just 1.5 meters above that same surface, at about head height, the temperature would be closer to 0 or below, and in the shade, just a few steps away, it could be -40 or colder. This extreme temperature gradient, where the difference between your feet and your head could be 20, 30, even 60 degrees Celsius across just a couple of meters, creates something that sounds almost absurd but is completely real. A Martian afternoon can be, technically, above freezing at ground level, while simultaneously being lethally cold at standing height in the shade, with wind that carries almost no thermal energy but can still strip moisture and cause equipment to fail, and then the night comes. If you thought the daytime temperature swings were extreme, nighttime on Mars is something else entirely. Near the equator, temperatures can plummet to -73 degrees Celsius after dark. In the polar regions during winter, they can reach -125 degrees Celsius. These drops don't happen gradually the way they do on Earth, where our thick atmosphere acts like a thermal blanket, holding heat in for hours after the sun goes down. On Mars, the atmosphere can't do that. The heat radiates directly into space almost immediately after sunset. What this means for any habitat, any life support system, any mechanical component on a Mars mission is that everything must be engineered to withstand temperature swings of up to 140 degrees Celsius between midday and midnight every single sol. A sol, just to clarify, is what scientists call a Martian day. It's 24 hours and 37 minutes long, so about every 25 hours, your equipment goes from something approaching tolerable warmth to temperatures that would shatter most unprotected materials. Metals contract and expand with temperature. Seals and gaskets harden and crack. Electronic components drift out of calibration. Lubricants that work perfectly at room temperature become thick and useless at -80 degrees. The InSight lander, NASA's geophysical mission that operated on Mars from 2018 until its power finally faded in 2022, gave engineers invaluable data about how equipment behaves through those extreme thermal cycles. Some of what they found was sobering. Components behaved in ways that hadn't been fully predicted by models, even models built on decades of spaceflight experience. Now scale that engineering challenge to a crude habitat, to the systems keeping human beings warm, keeping their air breathable, keeping their water liquid, keeping their food from freezing. Every thermal cycle is another stress test on every seal, every joint, every wire, every valve. And if a critical seal fails on a cold Martian night, the consequences are not a maintenance call. They're not a warranty claim. The consequences are that the people inside stop being people. Let's talk about the dust storms. Because this is where the temperature story and the dust story merge into something genuinely terrifying, and where Mars shows you a face that is unlike anything else in the inner solar system. Mars experiences local dust storms fairly regularly. Seasonal storms are common, But what Mars is uniquely capable of, in a way no other rocky planet we know of can match, are global dust storms, events where the entire planet becomes enveloped in a reddish-brown haze of suspended particles from pole to pole, lasting for weeks or even months. The most famous recent example is the global dust storm of 2018. It began as a regional storm in late May of that year and expanded with terrifying speed. By June, it had grown to cover an area larger than North America. By July, it had become truly global. The opacity of the Martian atmosphere, measured by a value called tau, reached levels so high that it blocked most of the sunlight reaching the surface. Solar-powered spacecraft lost power. Surface temperatures dropped, and the Opportunity rover, which had operated brilliantly for nearly 15 years, went to sleep waiting for sunlight that never came in sufficient quantity. It never woke up again. Now imagine you are a human being on the surface during a global dust storm. Your solar panels, if that's part of your power system, are producing a fraction of their normal output. The dust is coating every exterior surface. Visibility outside drops to near zero. You cannot go outside for an EVA without risking getting your suit clogged with fine particulate matter. The perchlorate-laced dust is in the air, in concentrations that would concern you deeply if any of it found its way into your habitat. And the storm could last for 3 months. Confined to your habitat, watching your power reserves decline, rationing food because you can't grow anything under that sky, watching the dust accumulate against your windows centimeter by centimeter until the outside world disappears entirely. There's a psychological dimension to this that science is only beginning to properly quantify, and we'll get to that in detail in a later section. But let's stay with the physical reality of dust storms for one more moment, because there's a piece of this story that most people don't hear. Global Martian dust storms are driven partly by a phenomenon called positive feedback, a self-reinforcing cycle where the suspended dust heats the atmosphere, which increases wind speeds, which lifts more dust, which heats the atmosphere further. The whole thing can escalate from a regional storm to a planetary one surprisingly quickly. We have observed this process from orbit with missions like the Mars Reconnaissance Orbiter, which has been watching the planet continuously since 2006. The data is extraordinary and a little humbling, because even after all these years of observation, we still cannot reliably predict exactly when a global storm will start, how severe it will get, or precisely when it will end. That's not a knock on the scientists. The atmosphere of Mars is genuinely complex in ways that continue to surprise researchers. The dust cycle interacts with the water ice cycle, with surface topography, with seasonal pressure changes as carbon dioxide freezes out at the poles in winter and sublimes back into the atmosphere in spring. It's a dynamic system, and dynamic systems resist simple prediction. For a crewed mission, that unpredictability is a serious operational problem. You cannot plan around an event that gives you limited warning and could last anywhere from a few weeks to several months. You can only build margins wide enough that you survive the worst case. And the worst case on Mars, as we've seen, has a way of being worse than the model. Now here's something that connects the dust, the temperature swings, and the radiation in a way that most people haven't thought about. They don't act independently, they stack, they compound, they interact with each other and with the human body in ways that are not simply additive. Consider this. You're a crew member on a Mars surface mission. You've been there for 4 months. Your bones have been slowly losing density because Martian gravity is only about 38% of Earth's. We'll come to bone loss in detail shortly, and it's alarming. Your gut microbiome has been shifting because the radiation is affecting the cells lining your intestines. You're sleeping poorly because the light cycle on Mars is close to Earth's but not quite right, and your circadian rhythm is subtly but persistently off. You've been breathing recycled air with a slightly different composition than Earth's. You've been eating food that was grown under artificial light or came out of a package. Your immune system is under chronic low-level stress, and then the global dust storm hits. Your power drops, you're confined, you're rationing. The temperature inside your habitat is harder to maintain because the thermal management system is working against an environment that just became even more extreme. The psychological pressure spikes. This is what researchers call a cascade scenario, where multiple moderate stresses compound into something that overwhelms a system's ability to cope. Cascade scenarios are exactly what accident investigators find at the heart of most major catastrophic failures. From aviation disasters to reactor meltdowns, the individual components were all manageable. It was the convergence that became fatal. On Mars, the environment is specifically designed by physics, not by malice, just by physics, to create exactly those convergence conditions. I want to pause here because something we just touched on deserves its own full treatment. 38% gravity. That number sounds almost gentle. You'd weigh about a third of what you weigh on Earth. You'd be able to jump higher, carry heavier things with less effort, move through the landscape with a lightness that sounds almost appealing. But your body doesn't experience reduced gravity as a gift. It experiences it as a catastrophe in slow motion. We know this from studying astronauts on the International Space Station, which orbits Earth in microgravity, essentially zero gravity. After just 6 months in microgravity, astronauts return to Earth with measurable bone density loss, muscle atrophy, fluid shifts in their bodies, changes to their eyesight caused by increased intracranial pressure, and alterations to their cardiovascular systems. After 12 months, as NASA's twin study, with astronaut Scott Kelly, documented in extraordinary detail, those changes are even more pronounced, and some of them take years to fully reverse. Mars' gravity is not zero, it's 38% of Earth's. That's significantly better than the International Space Station environment. But, and this is critical, it is nowhere near enough to preserve normal human physiology over time. We simply do not have direct data on what happens to the human body over months and years in Martian gravity specifically. We have the microgravity data, we have models, we have simulations, but no human being has ever spent an extended period in 38% gravity. It is one of the most significant gaps in our biomedical knowledge for Mars exploration, and the scientists who study this are candid about how much uncertainty remains. What the models suggest is that bone loss and muscle atrophy will still occur on Mars, though probably more slowly than in full microgravity. But more slowly over 1 Martian year, nearly 2 Earth years, could still mean a level of physiological degradation that significantly compromises a crew member's ability to perform the physical tasks a Mars mission demands. Drilling, hauling, repairing equipment, responding to emergencies. On a planet where physical capability could be the difference between life and death, that degradation is not abstract. It is operational risk of the highest order. And then there is the question of what happens if someone gets sick, not from radiation, not from perchlorates, just sick, a respiratory infection, a broken bone from a fall on the uneven Martian terrain, an appendicitis, a dental abscess that turns into a serious infection, the kind of medical event that here on Earth you handle by going to a clinic or a hospital. On Mars, in the first decade or more of human exploration, there will be no clinic, no hospital, no surgeon on call, no ability to evacuate a critically ill crew member back to Earth, because the geometry of planetary orbits means that for most of the time a crew is on Mars, Earth is simply not accessible. A return journey cannot be launched on demand. You have to wait for the planets to align in the right configuration, and that happens on a roughly 26-month cycle. 2019 paper in the journal NPJ Microgravity outlined the medical challenges of long-duration deep space missions with remarkable clarity. The authors noted that even with sophisticated onboard medical systems, there are interventions that cannot realistically be performed without specialized training and equipment that current mission architectures cannot fully accommodate. The further you are from Earth, the more the crew must become self-sufficient medically, and the limits of that self-sufficiency in the event of a serious acute medical crisis are genuinely frightening. We've now walked through the atmosphere, the radiation, the temperature extremes, the dust storms, the toxic soil, the gravitational physiology, and the medical reality. And we are not even halfway through everything Mars has prepared for you. In Part 3, we're going into something that I personally find one of the most fascinating and disturbing aspects of this entire story: what extended isolation and confinement does to the human mind, and what the real psychological research from analog missions tells us about the mental limits of a Mars crew. Studies from places like the High Seas habitat in Hawaii, the Mars 500 isolation experiment in Moscow, and Antarctic winter rover research have produced findings that are genuinely startling, because it turns out that the most dangerous thing on Mars might not be outside the habitat at all. It might be the people inside it. There is a building in Moscow that most people have never heard of. From the outside, it looks like a fairly unremarkable research facility. No windows facing outward, no dramatic architecture. Nothing to suggest that what happened inside it between 2010 and 2011 was one of the most psychologically demanding experiments ever conducted on human beings outside of actual spaceflight. The project was called Mars 500, and what the researchers did was seal 6 volunteer crew members, 3 Russians, a Frenchman, an Italian Colombian, and a Chinese national, inside a series of interconnected metal modules for 520 days. That's roughly 17 months. The modules together had a total habitable volume of about 550 cubic meters. They had no natural light, no fresh air from outside, no ability to leave. Communication with the outside world was subject to a built-in delay that grew progressively longer as the simulated mission moved further from Earth, eventually reaching a 20-minute one-way delay, meaning a full 40 minutes between asking a question and receiving an answer. The goal was to simulate, as faithfully as possible on Earth, the psychological conditions of a crewed mission to Mars. What they found was not reassuring. By the midpoint of the experiment, roughly 8 or 9 months in, several of the crew members were showing measurable changes in their sleep patterns, not just sleeping differently, but showing signs of what researchers classified as a kind of chronic low-grade sleep disorder, where the boundary between wakefulness and sleep was becoming blurred. Some crew members were spending up to 24 hours without meaningful activity. The physical activity levels of the group dropped substantially compared to the early mission phase. There were periods of what the researchers described as sedentary inactivity, long stretches where crew members were essentially doing very little, not because they had nothing to do, but because the motivation to do it had quietly drained away. This is not laziness. This is not weakness of character. This is a well-documented psychological phenomenon called psychological hibernation, a kind of adaptive withdrawal response that the human mind uses when it perceives that it is trapped in an environment with no meaningful external stimulation and no clear prospect of change. Your brain, at some level, concludes that conserving energy is the rational response to a situation that isn't going to meaningfully improve. And so it starts to power down non-essential functions. Curiosity, initiative, social engagement, emotional responsiveness. The Mars 500 researchers were careful to note that no crew member experienced a full psychological breakdown. The mission completed its timeline, but the cognitive and behavioral changes they documented, the withdrawal, the sleep disruption, the declining motivation, were consistent and measurable, and critically, they appeared even in a simulation where the crew knew they were on Earth, knew they could exit in a true emergency, and had the psychological reassurance that their families were just outside the building. Remove that reassurance, add genuine mortal danger, add the knowledge that if something goes wrong, no one is coming to help. Add a 20-minute communication delay that makes any real-time conversation with loved ones impossible. Add the sounds and sensations of a genuinely alien world pressing against the walls of your habitat. And then ask yourself what 520 days does to a person. The HICS studies, the Hawaii Space Exploration Analog and Simulation missions conducted on the slopes of Mauna Loa volcano approached the psychological question from a different angle. Between 2013 and 2017, NASA funded a series of missions where small crews lived in a dome-shaped habitat at about 2,500 meters elevation on the volcanic slopes in a landscape that is about as close to Mars-like terrain as Earth offers. Missions ranged from 4 months to a full year in duration. The findings from the longer missions in particular revealed something that has become a significant concern in Mars mission planning circles: the problem of crew cohesion breakdown. In the early phases of a long-duration mission, crews tend to be highly cooperative. Motivation is high. The novelty of the situation is still engaging. Everyone is performing their role with enthusiasm. But as the months accumulate, something shifts. Interpersonal tensions that were manageable in the early weeks begin to calcify into something harder. Small irritations become significant grievances. Communication patterns change. Crew members talk less or talk differently, with more guarded language and fewer genuinely open exchanges. Subgroups form. In some cases, a single crew member becomes socially isolated from the rest of the group, not through any dramatic conflict, but through the gradual accumulation of small social friction. Researchers call this the third quarter phenomenon, a documented pattern in isolated, confined environments where the most difficult psychological period tends to occur roughly 3/4 of the way through a mission, when the end is visible but still far enough away that it feels almost unreachable. Antarctic winter over crews show it, submarine crews show it, the high seas crews showed it, and a Mars crew would face it at a point in the mission when operational demands are still at their peak. Now, here's the part that I think is genuinely underappreciated in public discussions about Mars missions. The psychological risks don't just affect crew well-being, they affect mission safety in ways that are direct and potentially catastrophic. Most serious incidents in aviation, in nuclear operations, in submarine service, and in other high-consequence isolated environments have a human factors component. Poor communication, fatigue-driven errors, conflict that disrupted coordination at a critical moment. Decisions made by people who were cognitively degraded in ways they may not have been fully aware of. A Mars crew operating after 10 or 12 months on the surface, dealing with radiation exposure, sleep disruption from the slightly off-kilter Martian day, the physiological effects of reduced gravity, chronic low-level nutritional stress from a limited and repetitive diet, and the psychological weight of isolation is not operating at peak cognitive capacity. They are making critical decisions about life support systems, EVA safety, equipment maintenance, and resource management while their brains are running on fumes. A 2019 study in the journal Frontiers in Physiology that analyzed data from astronauts aboard the International Space Station found measurable cognitive performance decrements over long-duration missions, particularly in the domains of spatial orientation and processing speed. These are not trivial skills in a Mars environment. Spatial orientation matters when you're navigating the Martian surface in a suit, managing your distance from the habitat, making sure you know exactly where you are in terrain that has no landmarks and no GPS. Because Mars has no GPS constellation, a detail that will come up again later when we talk about navigation. Processing speed matters when something goes wrong, and something will go wrong. Not necessarily something catastrophic, but a sensor alarm, a suit integrity warning, a life support anomaly. In those moments, you need your brain to work at full speed, and after a year on Mars it won't be. There is another layer to this that goes beyond what any laboratory simulation has been able to fully capture, and it comes down to something almost philosophical, something that strikes at the heart of what it means to be a human being in the universe. We are profoundly, deeply, evolutionarily adapted to Earth. Every sense you have was shaped by 4 billion years of life on this planet. Your eyes evolved to see in Earth's light. Your ears evolved to hear in Earth's air. Your sense of smell evolved in response to Earth's chemistry. Your circadian rhythm is tuned to Earth's 24-hour day. Your immune system learned its repertoire of responses in the microbial ecosystem of Earth. Your brain's deep emotional architecture, the parts that generate feelings of safety, of belonging, of home, were built for Earth. Mars offers none of those cues, none of them. The light is wrong. The sun seen from Mars is only about 43% as bright as it appears from Earth, and it has a slightly bluish tint during the day, because of the way the Martian dust scatters the longer wavelengths of red light during high poach conditions. Sunrise and sunset on Mars, paradoxically, appear blue, the inverse of Earth, where the sky is blue and the sunsets are red. The Martian sky during the day is not blue. It's a butterscotch tan, sometimes pinkish, sometimes brownish, depending on dust levels. There is no wind sound that carries any familiar resonance. The Martian atmosphere is so thin that sound travels differently. Higher frequencies attenuate faster, meaning the world on Mars is both quieter and missing certain tones that we've been hearing our entire lives without ever thinking about them. The Ingenuity helicopter, NASA's small rotorcraft that flew on Mars beginning in 2021, produced audio data that allowed scientists to study Martian acoustics directly. The resulting recordings, when shared publicly, produced a reaction among listeners that many described not just as scientifically interesting but as deeply unsettling. The sounds of Mars felt, to human ears, subtly wrong in a way that's difficult to articulate but immediately felt. Imagine living in that sensory environment for a year, not visiting it, living in it, sleeping in it, waking up in it every morning, having no alternative to it. Astronauts on the International Space Station can look out the window and see Earth. They can see the blue oceans, the white clouds, the green and brown continents rolling beneath them. Multiple astronauts have described this experience, called the overview effect, as transformative and deeply emotionally stabilizing. Even when the work is grueling, even when they're exhausted, even when interpersonal tensions are high, the sight of Earth hanging in space provides something fundamental, a reminder of home, a reminder of beauty, a reminder of what they're connected to. From Mars, Earth is a point of light. On the best nights, it's one of the brightest objects in the Martian sky, a pale blue dot, as Carl Sagan so perfectly described it when Voyager 1 photographed our planet from beyond the orbit of Neptune in 1990. From Mars, Earth is even smaller than that. You can cover it with the tip of your finger. Everyone you have ever loved, every place you have ever been, every sound, smell, and feeling that means home to you. A tiny, cold, unreachable dot of light in an alien sky, and you know with complete certainty that you cannot go home, not for another year at least, maybe longer if the mission extends, maybe never if something goes wrong, maybe never, depending on decisions made by mission planners and orbital mechanics that are entirely outside your control. That knowledge, sitting in the back of every crew member's mind every single day for the duration of the mission, is a psychological weight that no analog study has ever been able to fully replicate, because in every analog study, going home was always an option. On Mars, it isn't. The communication delay deserves a full moment of attention here, because it is one of the most practically disruptive aspects of the Mars mission scenario, and one that is chronically underestimated by people who haven't thought it through carefully. The distance between Earth and Mars varies enormously as the two planets orbit the Sun. At closest approach, what astronomers call opposition, Mars can be as close as about 54.6 million kilometers from Earth. At their most distant, they can be separated by over 400 million kilometers. The communication delay, the time it takes a radio signal traveling at the speed of light to cross that distance, varies accordingly, from about 3 minutes at closest approach to about 24 minutes at maximum separation. 3 minutes doesn't sound so bad, but consider what it means in practice. If you have a medical emergency and you radio Earth for advice, you wait at minimum 6 minutes for a response. 3 minutes for your signal to arrive, 3 minutes for the reply to come back. And that's at closest approach. At average distances, you're looking at anywhere from 8 to 20 minutes each way. At maximum distance, nearly 50 minutes round trip. Now consider a fast-moving emergency, a suit failure during an EVA, a fire in the habitat, a pressure loss, a crew member going into cardiac arrest. In any of those scenarios, the outcome is determined in minutes, sometimes in seconds. There is no time to call Earth and wait for advice. There is no time for mission control to evaluate the situation and talk you through a solution. You are on your own, completely, entirely, irrevocably on your own. This is not a solvable problem through better technology. It is a consequence of the physics of the universe, of the finite speed at which information can travel. Mars is simply too far away for real-time support to be possible. A Mars crew must be capable of handling every conceivable emergency entirely from their own knowledge, training, and resources. And that level of self-sufficiency, truly complete, truly independent self-sufficiency, is something that has never been demanded of any human beings in the history of exploration. Even Antarctic expeditions, even submarine patrols, even the Apollo missions had response options, communication systems, and intervention possibilities that a Mars crew will not have. By now, you might be thinking, okay, all of this is real and all of it is serious, but humans are resilient. We adapt. We have survived extraordinary hardships throughout history. We crossed oceans in wooden boats. We built cities in deserts. Surely we can find a way to handle the psychological demands of a Mars mission, and here's my honest answer to that. Maybe, possibly, with the right crew selection, the right training, the right habitat design, the right psychological support systems, the right mission architecture, maybe. Human beings are genuinely remarkable. Our adaptability is one of the most extraordinary things about our species. But maybe is not a mission design criterion. Maybe doesn't get you through a global dust storm when your power reserves are at 30% and 2 of your crew members haven't spoken to each other in 3 weeks and someone is running a fever. And the communication delay means Earth won't know what's happening here for another 20 minutes. What gets you through that is preparation and redundancy and a depth of understanding about the risks that is so complete, so honest, and so clear-eyed that nothing surprises you. Not the cold, not the dust, not the silence, not the loneliness, not the weight of being the furthest human beings from home that have ever existed. And that understanding starts here, with what Mars actually is, not what we hope it might be, not what makes for a good headline. What it actually, physically, chemically, psychologically is If you are enjoying this journey, make sure to subscribe to the channel. Every video we tackle the questions that actually keep you up at night. And we never come back empty-handed. Now we're going somewhere even more specific and in some ways even more alarming. We're going to talk about what Martian gravity does to your cardiovascular system, your bone structure, and your vision over the course of a year. Because the data from long-duration spaceflight is telling us things about human physiology in reduced gravity that the first Mars mission planners are going to have to confront head-on. Some of those findings are extraordinary, some of them are deeply concerning, and one of them involves the human eye doing something that nobody fully predicted until astronauts started coming back from long missions and having their vision checked. Let's explore that story now. And once you hear it, you will never look at the phrase long-duration spaceflight the same way again. Let's start with your eyes. Not because they're the most dramatic physiological threat a Mars mission poses, they're not, but because what happens to human vision during long-duration spaceflight is one of the most unexpected, most well-documented, and in many ways most instructive discoveries to come out of the entire International Space Station program. It is a story that began with astronauts quietly mentioning that their eyesight seemed a little off after a few months in orbit, and it ended with researchers discovering a fundamental, previously underappreciated conflict between the human body and the absence of normal gravity. The condition is called spaceflight-associated neuroocular syndrome. Scientists acronym it as SANS. And when you understand what's actually happening inside the skull of an astronaut experiencing it, the elegance of the problem is almost as striking as its danger. Here's the mechanism. On Earth, gravity pulls your body's fluids downward. Your blood, your cerebrospinal fluid, the fluid that surrounds and cushions your brain and spinal cord, all of it is constantly being pulled toward your feet by one full gravity. Your cardiovascular system has spent your entire life compensating for this, pumping hard enough to get blood up to your brain against that gravitational pull. Your lymphatic system, your venous drainage, your entire circulatory architecture is designed around the assumption that down is down. In microgravity, there is no down. Fluids shift toward the head. Astronauts famously describe the feeling in the first days of spaceflight as similar to having a permanent head cold. Their faces puff up, their nasal passages feel congested, and they experience a persistent fullness in their heads. Most of them adapt to this over a few weeks and stop noticing it consciously, but the fluid shift doesn't stop. It continues throughout the mission, and the consequences over months become structural. The cerebrospinal fluid that surrounds your brain normally drains efficiently because gravity assists the process. In microgravity, that drainage becomes less efficient. The pressure of the cerebrospinal fluid around the brain, what doctors call intracranial pressure, increases, and the optic nerve, which connects your eye to your brain, passes through the skull via a channel called the optic canal. The back of your eyeball sits right at the point where that channel meets the inside of the skull. When intracranial pressure rises chronically, over months in a microgravity environment, it begins to press on the optic nerve sheath. The optic disc, which is the point at your retina where the optic nerve enters the eye, begins to swell. The eyeball itself can change shape, flattening slightly at the back, which alters the focal length of the eye and causes farsightedness. In more severe cases, the increased pressure can cause small folds to develop in the choroid, the layer of blood vessels behind the retina. NASA's twin study, which compared astronaut Scott Kelly after his year aboard the International Space Station with his identical twin brother Mark Kelly, who remained on Earth, documented SANS changes in Scott Kelly's eyes clearly. His optic disc showed swelling, his eyesight had measurably shifted, And critically, not all of those changes had fully reversed 2 years after his return to Earth. Other astronauts have experienced similar findings. A 2019 study in the journal JAMA Ophthalmology analyzed data from 318 astronauts and found that among those who had been on long-duration missions, 6 months or more, a significant proportion showed at least some of the hallmark features of SANS. Now, Mars gravity is 38% of Earth's. It is not microgravity, and there is genuine, cautious scientific hope that 38% gravity will provide enough of a downward fluid drainage, assist to reduce or eliminate the SANS problem. But here is the honest scientific position. As of today, we do not know. We have never had a human being spend months in 38% gravity. We cannot run that experiment on Earth. We cannot fully replicate it on the International Space Station. The only way to find out what 38% gravity does to intracranial pressure and optic nerve health over a year is to send someone to Mars and find out. That is not a comfortable position to be in when we're talking about the permanent vision health of astronauts. Let's move from your eyes to your bones. Because this story is older than SANS, better understood, and in some respects even more alarming for a Mars mission specifically, bone is not inert material. It is living tissue constantly being broken down and rebuilt by 2 types of specialized cells, osteoclasts, which dissolve old bone material, and osteoblasts, which build new bone. On Earth, the mechanical loading that gravity places on your skeleton, the simple act of standing, walking, carrying your body weight against gravity, sends constant signals to your bones to maintain their density and structure. Take that loading away, and the balance between breakdown and rebuilding shifts. Osteoclasts become more active, osteoblasts become less active. Bone density falls. In microgravity, astronauts lose bone density at roughly 1 to 2% per month in weight-bearing bones. The hips, the spine, the femur. 6 months on the International Space Station can produce bone density losses equivalent to decades of normal aging on Earth. The exercising protocols on the ISS, astronauts are required to exercise roughly 2 hours per day using specialized resistance equipment, have significantly reduced but not eliminated this bone loss. On Mars, exercise will be possible in a way it isn't in microgravity. Walking on the surface in 38% gravity does load the bones. More than floating in zero gravity, certainly. But 38% is still only 38%. The bones of a Mars crew member will be receiving roughly 62% less gravitational loading than their skeletons evolved to need. Over a year, that matters enormously. Fractures become a serious concern. Not just from acute trauma, a fall on the uneven Martian surface, but from what doctors call stress fractures, the kind that develop when bone that has lost density is subjected to repeated mechanical loading. A crew member who has been on Mars for 10 months with measurably reduced bone density in their hips and spine, undertaking a physically demanding EVA on challenging terrain, is at real risk of a fracture that on Earth would be a medical inconvenience and on Mars would be a potential mission-ending crisis. And we haven't yet developed a pharmacological intervention that reliably prevents bone loss in reduced gravity environments over timescales of a year or more. Bisphosphonate drugs, which are used on Earth to treat osteoporosis, have been tested in spaceflight contexts and show some promise. But their long-term use comes with its own risks and side effects. There is no clean solution. There is no pill you take that makes your skeleton behave as though gravity is normal when it isn't. Muscle atrophy runs parallel to bone loss, and the two interact in ways that compound the problem. Your muscles, like your bones, depend on gravitational loading to maintain their mass and function. In reduced gravity, muscles that are used less, particularly the postural muscles of the back, the hip flexors, the quadriceps, all the muscle groups that work hardest on Earth to keep you upright against gravity begin to atrophy. They lose mass, they lose strength, they lose the specific fiber composition that makes them suitable for sustained physical effort. On the International Space Station, despite 2 hours of daily exercise, astronauts return to Earth with significant muscle mass losses, particularly in their legs, and many describe the experience of walking again after 6 or 12 months in orbit as startlingly difficult. Their legs feel like they belong to someone else. Their balance is compromised. Their endurance is a fraction of what it was before the mission. The transition back to full Earth gravity after a long ISS mission is carefully managed precisely because of these physiological changes. Crew members are caught by waiting personnel when they exit the Soyuz capsule. They are carried, not walking, to initial medical evaluations. They spend weeks in structured rehabilitation before their physiology has recovered enough to function normally. On Mars, there is no rehabilitation team waiting. There is no recovery period in a properly equipped facility. The mission continues. The demands of the surface continue. If you need to respond to an emergency on month 11 of your Mars stay, if you need to move quickly, carry something heavy, perform a physically demanding task under time pressure, you will need to do it with a body that has been in 38% gravity for nearly 2 years, if you count the transit time. A body that is measurably weaker, lighter of bone, and less physiologically capable than the one that left Earth. There is another physiological system that reduced gravity and the spaceflight environment affects, and it is one that most people don't think about until it's explained to them, and then it immediately seems obvious. That system is your cardiovascular system, specifically your heart. Your heart is a muscle. Like all muscles, it responds to the demands placed on it. On Earth, your heart works against gravity constantly, pumping blood upward to your brain, maintaining pressure throughout a circulatory system that has to push fluid vertically through a body standing upright in one gravity. That work keeps the heart strong, keeps the cardiac muscle conditioned, keeps the whole system calibrated to the demands of life in one gravity. In microgravity, the heart's workload changes, with fluids shifting toward the head and no gravitational gradient to pump against. The heart doesn't have to work as hard to maintain adequate cerebral perfusion. Over time, it adapts. The cardiac muscle loses some of its conditioning. The heart can actually change shape slightly. Multiple studies have documented a tendency toward a more spherical cardiac geometry in long-duration microgravity. And perhaps most concerningly, the total blood volume in the body decreases. The body essentially reads the fluid shift toward the head as a signal that there's too much fluid in the upper body, and it downregulates blood production accordingly. Return to full gravity after this adaptation, and your cardiovascular system is suddenly being asked to perform its original task, pushing blood upward against gravity with a heart that has been deconditioning and a reduced total blood volume. It manages, but it struggles, particularly in the first weeks after return. Orthostatic intolerance, the tendency to feel faint when standing up, is extremely common in returning astronauts, and in some cases persists for months. On Mars, you arrive after a transit that has already subjected your cardiovascular system to months in microgravity during the journey. Your heart, your blood volume, your circulatory architecture have all adapted to zero gravity by the time you land. And now you step out onto the Martian surface in 38% gravity, more than zero, but still far less than Earth. And your cardiovascular system has to adapt again. It will, but that second adaptation takes time, and during that transition period, your physical capacity is at its lowest point of the entire mission. Here's something I find genuinely remarkable about all of this, and I want to take a moment to share it because it speaks to something deeper than just the immediate survival challenges. every single physiological problem we've discussed. The fluid shift, the bone loss, the muscle atrophy, the cardiovascular deconditioning is not a design flaw in the human body. It is the human body doing exactly what it evolved to do, adapting efficiently to its environment, conserving resources that aren't being used, redistributing effort based on the demands being placed on it. We are the products of 4 billion years of biological evolution on a planet with a specific gravitational field, a specific atmospheric composition, a specific magnetic field, a specific solar radiation environment, a specific day length, and a specific ecological context. Every cell in your body is tuned to those specific parameters. We are not a general-purpose biological system that can be deployed anywhere in the solar system with minor modifications. We are an Earth organism, profoundly, specifically, beautifully an Earth organism. And Mars is not Earth. It is not close to Earth. It is not a rougher version of Earth that we just need to adapt to with better gear. It is a fundamentally different world, operating under fundamentally different physical conditions, and every day spent there is a day spent asking an Earth body to do something it was simply not built to do. That's not a reason not to go. I want to be clear about that. The science of human spaceflight is advancing. The engineering solutions being developed are genuinely impressive. The human drive to explore, that restless, magnificent, quintessentially human impulse to go further, to see what's over the next horizon, that drive has carried us to every corner of this planet and beyond. It is one of the most beautiful things about our species, but it is a reason to go with absolute clarity about what we're asking of the people who go, and it's a reason to be honest, deeply, unflinchingly honest, about what the data currently tells us. We've now covered eyes, bones, muscles, and the cardiovascular system, but there are two more physiological systems that the Mars environment affects in ways that are still being actively researched, and both of them are going to surprise you. The first is your immune system, and the second is your brain itself, not just cognitively, not just psychologically, but structurally. Because data from long-duration spaceflight is now suggesting that the brain physically changes during extended missions in ways that researchers are still trying to fully understand. Changes in the volume of certain brain regions, changes in the distribution of white matter, changes in the fluid spaces around the brain that persist long after the astronaut has returned to Earth. We'll get to both of those in Part 5. And we'll also get to something that connects all of these physiological threads back to the bigger picture. Because everything we've been discussing, every way Mars threatens the human body, is also, from a different angle, a remarkable story about what Earth does for us every single day without us ever having to ask. We live on a planet that is, by any honest cosmic measure, extraordinarily well suited to our existence. And sometimes it takes the brutal hostility of another world to make you feel the full weight of that extraordinary gift. Our immune system has a memory, not a metaphorical memory, a literal biological, molecular memory. Every pathogen your body has ever encountered, every virus, every bacterium, left behind a population of specialized cells called memory lymphocytes. These cells persist in your body for years, sometimes decades, sometimes for life. They are your immune system's archive, its accumulated experience, its learned knowledge of what is dangerous and how to fight it. That archive was built on Earth. Every entry in it was written by an encounter with an Earth organism, in an Earth environment, under Earth conditions. And like every other system in your body, your immune system doesn't just store information, it constantly maintains itself, recalibrates itself, and draws on signals from the environment to stay appropriately tuned. One of the most important of those environmental signals is microbial exposure. The trillions of microorganisms that live in and on your body, your microbiome, are not just passengers. They are active participants in your immune system's ongoing calibration. Your gut microbiome alone contains somewhere in the range of 38 trillion microbial cells, roughly equal to the number of human cells in your body. Those microorganisms produce compounds that regulate immune cell development, influence inflammatory responses, and help maintain the boundary between appropriate immune activation and the kind of overreaction that causes autoimmune disease. On Mars, your microbiome is going to change profoundly and probably irreversibly over the course of a year. The habitat you live in on Mars will be a closed system. The air is recycled, the water is recycled. The surfaces are regularly sanitized to prevent the buildup of potentially dangerous microbial contamination. The food is either pre-packaged from Earth or grown in a highly controlled hydroponic environment. There are no wild spaces, no soil underfoot, no wind carrying pollen and spores and the invisible biological richness of an outdoor world. No animals, no casual contact with the vast, diverse, constantly shifting microbial ecosystem that surrounds every human being living on Earth. Studies of isolated environments, Antarctic stations, submarines, sealed research habitats consistently show that microbial diversity in the environment and in the people living there decreases over time. The same strains cycle repeatedly through the small closed population. New inputs stop arriving, and as the microbial environment simplifies, the immune systems of the people living in it respond in ways that are still being studied but are clearly not neutral. The data from the International Space Station is particularly striking. Research published in journals including Microbiome and Cell has documented measurable shifts in astronaut gut microbiome composition during long-duration missions. The diversity of microbial species in the gut decreases. The relative abundance of certain bacterial groups shifts in ways that have been associated, in terrestrial studies, with increased inflammatory tone and altered immune function. Simultaneously, the immune system itself shows changes in spaceflight that are not simply explained by microbial shifts. Natural killer cell activity, the frontline immune response against virally infected cells and early cancer cells, is reduced in astronauts during long-duration missions. The distribution of T-cell populations changes. Inflammatory markers in the blood shift, and perhaps most concerning of all, latent viruses like the Epstein-Barr virus, the herpes simplex viruses, and the varicella zoster virus that causes chickenpox and shingles, begin to reactivate. Viral reactivation is something that happens on Earth too. Most adults carry dormant herpes family viruses that their immune systems keep suppressed through constant low-level surveillance. When the immune system is stressed by illness, by sleep deprivation, by psychological stress, by corticosteroid treatment, that surveillance weakens momentarily and the viruses take the opportunity to replicate. The result is a cold sore or a bout of shingles, or a recurrence of symptoms the person thought they'd left behind years ago. In astronauts, viral reactivation rates are significantly elevated compared to their pre-flight baselines. A study published in 2019 in Frontiers in Microbiology, drawing on samples collected from astronauts on short shuttle missions and long-duration ISS missions, found that herpes viruses were being shed, excreted from the body in saliva and urine, indicating active replication at substantially higher rates during flight than before or after. For most of the astronauts studied, this reactivation didn't produce clinical symptoms. The immune system was weakened enough to allow replication, but not weakened enough to permit a full symptomatic outbreak. But the trend line is not reassuring when you project it forward. A one-year mission on Mars, with all of the cumulative stresses we've discussed, radiation, psychological pressure, sleep disruption, nutritional limitations, reduced gravity effects, and microbial impoverishment, represents an immune challenge of a different order of magnitude than a 6-month ISS mission. And if an immune system compromised enough to allow significant viral reactivation is also the immune system that has to respond to a novel medical emergency, an infected wound from an EVA accident, a respiratory infection spreading through the crew, a post-surgical recovery, the margins become very thin very quickly. Medical capability on Mars will be limited by definition. You cannot pack a fully equipped hospital into a habitat that has to be launched from Earth and traveled across interplanetary space. You cannot bring an entire pharmaceutical formulary. You cannot bring the diagnostic imaging equipment, the specialist expertise, the intensive care infrastructure that modern medicine relies on. Whatever medical capability the crew has will be what was packed before departure, maintained by the crew members who have medical training as part of their broader skill set, and constrained by the communication delay that prevents real-time guidance from Earth-based physicians. A serious infectious illness, pneumonia, a deep wound infection, a gastrointestinal infection spreading through the crew. In an immunocompromised Mars crew, 12 to 20 minutes from the nearest medical consultation and an average of roughly 225 million kilometers from the nearest hospital is a scenario that mission planners spend a great deal of time thinking about, as they should. Now, let's talk about your brain, not the psychological dimension we covered in Part 3, the loneliness, the cognitive fatigue, the motivation erosion. Those are real and serious. But what I want to talk about now is different. What I want to talk about is structural, physical, the actual tissue of your brain changing in measurable ways in response to an environment it was not designed for. The data started coming in from NASA's long-duration mission research in the mid-2010s, and it was, to put it plainly, unexpected. Researchers performing MRI scans on astronauts before and after long-duration missions began noticing something that didn't fit neatly into any existing model of spaceflight physiology. The brain was moving, not dramatically, not in a way that caused immediate symptoms in most cases, but measurably, consistently. The brain was shifting upward within the skull, displaced by the same fluid shift that causes sands in the eyes. The cerebrospinal fluid spaces at the top of the brain, called the sulci, were narrowing because the brain was being pushed upward against the top of the skull. The fluid spaces at the base of the brain were expanding, and a structure called the central sulcus, a major groove in the brain surface that runs roughly from ear to ear across the top of the skull and separates the frontal lobe from the parietal lobe, was narrowing in a way that correlated with certain changes in motor function. A study published in the New England Journal of Medicine in 2017, led by a research team at the University of Texas Health Science Center, analyzed MRI data from 34 long-duration spaceflight astronauts and found that the majority showed measurable upward brain displacement. More striking, in many of the astronauts studied, this displacement had not fully resolved a year after return to Earth. The brain had shifted, and it was slow to shift back. Later research added further detail that raised the stakes considerably. Studies published in 2019 and 2020 began examining not just the position of the brain, but the composition of the white matter, the network of myelinated nerve fibers that connect different brain regions and carry signals between them. White matter changes in spaceflight have now been documented in multiple independent studies. The changes are subtle but detectable using advanced diffusion tensor imaging, which maps the microstructural organization of white matter tracts. What the data shows broadly is that the architecture of certain white matter pathways, particularly those associated with sensory processing and motor coordination, shows measurable alteration after long-duration missions. Some of these alterations persist at follow-up scans conducted more than a year after the astronauts' return, What do these changes mean functionally? That question is still being actively researched. Not all white matter microstructure changes are harmful. Some may represent adaptive reorganization rather than damage. But the honest answer is that we don't yet know with confidence what the long-term neurological implications are of spending a year in a reduced gravity, high radiation environment for the structural integrity of the human brain. And there's a specific radiation component to the brain story that deserves its own moment of attention. We talked in part 1 about the radiation environment on Mars, the cosmic rays and solar particle events that bombard the surface with an exposure rate of roughly 0.64 millisieverts per day. What we didn't fully explore then was what high-energy radiation does to the brain specifically, because the brain is not just another organ when it comes to radiation sensitivity. It is uniquely vulnerable in ways that matter enormously for a Mars mission. The brain is protected on Earth by the blood-brain barrier, a highly selective cellular barrier that controls what can pass from the bloodstream into the brain tissue. It keeps out pathogens, toxins, and many pharmaceutical agents, but high-energy particles, the kind that make up galactic cosmic radiation, pass through it without difficulty, and when they do, they interact with brain tissue in ways that are qualitatively different from the lower energy radiation we're more familiar with. Galactic cosmic rays include particles called heavy ions, atoms of iron, silicon, oxygen, and other elements that have been stripped of their electrons and accelerated to near-light speeds by distant supernovae. When one of these heavy ions passes through tissue, it leaves behind a dense track of ionization damage, a line of broken chemical bonds and disrupted cellular structures far more concentrated than the damage produced by X-rays or gamma radiation of equivalent dose. Research conducted at NASA's Space Radiation Laboratory at Brookhaven National Laboratory, using particle accelerators to simulate galactic cosmic ray exposure in animal models, has produced findings that the research team described as alarming enough to warrant significant attention. Studies published from 2015 onward in journals including Scientific Reports and Nature have shown that mice exposed to simulated galactic cosmic ray heavy ions show measurable deficits in spatial learning, memory, and anxiety regulation that persist long after the exposure. The mice show increased fearfulness, they show impaired performance in maze tasks that require spatial memory, and at the cellular level, their brains show evidence of neuroinflammation and dendritic regression. The neurons are literally losing some of their structural complexity. These are mice, not humans. Animal models are not perfectly predictive of human outcomes, but the biological mechanisms being identified, neuroinflammation, oxidative stress, disruption of synaptic architecture, are mechanisms that operate in human brains too, and the doses being used in the experimental work are within the range that a Mars crew would accumulate over a year on the surface. Put this together with everything else: radiation-induced neuroinflammation, white matter microstructure changes from fluid shifts and pressure effects, cognitive performance decrements from sleep disruption and psychological stress, immune-mediated inflammatory processes running at elevated baseline levels throughout the mission. All of these processes are happening simultaneously in the same brain, in the same person, for the same year. They don't happen in isolation, they interact. Neuroinflammation from radiation exposure and neuroinflammation from immune dysregulation run through overlapping molecular pathways. The cognitive effects of sleep disruption and the cognitive effects of radiation-induced neural changes compound each other. The human brain that arrives on Mars after 7 months in transit is not the same brain that left Earth. The brain that spends a year on the Martian surface is not the brain that made the journey there. And the brain that begins the 7-month return journey if there is a return journey, is carrying the accumulated neurological burden of everything we've described. Whether that brain is still capable of performing at the level required to fly a spacecraft, manage a re-entry, and navigate the final phases of the mission home is a question that mission planners are actively grappling with. The ISS data is reassuring in some respects. Astronauts do return from long missions and successfully resume complex cognitive tasks. But Mars is longer, farther, more radiative, and more isolated than any ISS mission. Extrapolating from ISS data to Mars conditions requires assumptions that we cannot yet validate. I want to pause here for a moment and acknowledge something, because I'm aware that everything in this script so far has been weighted heavily toward the risks, the dangers, the physiological and psychological costs of a Mars mission. And I want to be clear that this is not a pessimistic view of human spaceflight. It is not an argument against going to Mars. The scientists and engineers working on this are extraordinary people doing extraordinary work, and many of them believe that the problems we've discussed are solvable, that countermeasures will be developed, that mission architecture will be designed to minimize these risks, that the first Mars crew will be selected and trained and supported in ways that give them the best possible chance. I believe that too. But I also believe that the most respectful thing we can do for the science, for the mission, and for the people who might one day go, is to look at the full picture without flinching, to say clearly, this is what we know, this is what we don't know, this is where the data is concerning, this is where more research is needed. This is what it actually means to send human beings to Mars with the technology and knowledge we have today, because the alternative, the glossy, simplified version of Mars exploration that focuses only on the romance and the triumph and papers over the genuine dangers, does not serve anyone well. Not the public trying to understand what their tax dollars and their collective human ambition are being directed toward. Not the future crew members whose lives depend on mission planners having an accurate, complete picture of the risks, and not the science itself, which thrives on honesty and suffers from wishful thinking. Now we shift from the biological to the logistical, because surviving on Mars is not just about what your body can handle, it's about whether the systems that keep you alive can actually function reliably in the Martian environment for a full year. The life support systems, the power generation, the food production, the equipment that keeps the habitat pressurized and the air breathable and the water drinkable. And this is where things get genuinely fascinating in a different way, because the engineering challenges of a Mars habitat are as intellectually extraordinary as the biological ones. The solutions being developed are elegant and ambitious, but the margins are razor thin, and in a closed system, on a planet where resupply is not possible and the nearest repair shop is somewhere between 54 and 400 million kilometers away, razor-thin margins have a way of becoming the story. Let's start with a number, 4 kilograms. That is roughly how much consumable mass, food, water, oxygen, and other supplies a single human being requires per day to stay alive in a closed habitat in space. It's a number that NASA life support engineers work with constantly, because in the context of spaceflight, mass is not just a logistical inconvenience. Mass is money, mass is mission architecture. Mass is the difference between a mission that is theoretically possible and one that is actually achievable with existing or near-future launch technology. Multiply 4 kilograms by a crew of 4. Multiply that by 365 days. You get roughly 5,800 kilograms of consumables for a single year on the Martian surface. And that's before you account for the 7-month transit each way, the buffer stock for emergencies, or the mass of the systems required to process and recycle as much of that material as possible. Now consider that getting 1 kilogram of payload to the Martian surface currently costs, by various estimates, somewhere in the range of hundreds of thousands to millions of dollars, depending on the launch system and mission architecture. The economics alone make it immediately clear that a Mars crew cannot simply be resupplied from Earth the way a remote Antarctic research station can be resupplied by a cargo flight. Everything that crew needs, or as close to everything as engineering can achieve, has to either be brought from Earth before the mission begins or produced on Mars itself. This is the central engineering challenge of a Mars surface mission, and it is a challenge that ramifies outward into every corner of mission planning in ways that are worth understanding in detail. Start with water, because water is the most immediately critical resource, and because the water story on Mars is one of the most instructive examples of how a problem that sounds solvable in principle turns out to be genuinely difficult in practice. Mars has water. We know this with confidence now, and it represents one of the most significant scientific findings of the robotic exploration era. The Phoenix lander, which touched down in the Martian Arctic in 2008, directly confirmed the presence of water ice just below the surface. The Mars Reconnaissance Orbiter has mapped vast deposits of subsurface ice across the mid-latitudes. Radar data from the Mars Express and Marsis instruments have identified what appears to be liquid water, possibly briny liquid water, beneath the southern polar ice cap at a depth of about 1.5 kilometers. But here's the problem. That water is not accessible. The subsurface ice deposits that Phoenix confirmed are at depths of centimeters to meters. Extracting them requires drilling, excavating, heating the ice to sublimate or melt it, and then collecting and processing the resulting water, all in an environment where the temperature can drop to -70 degrees Celsius at night, where any exposed machinery must operate in near vacuum, and where the perchlorates we discussed in Part 1 contaminate the soil and would contaminate any water extracted from it without sophisticated processing. The putative liquid water under the southern polar cap, assuming those radar interpretations are correct, is approximately 1.5 kilometers underground and almost certainly so briny, so saturated with dissolved salts that it would require industrial-scale desalination equipment to render it usable. Equipment that would need to be landed, assembled, and operated on Mars before it could produce a single liter of drinkable water. The practical water strategy for the first Mars missions will almost certainly rely primarily on recycling, recovering water from every possible source within the habitat. Crew urine, processed and purified through a multi-stage filtration and chemical treatment system. Atmospheric humidity, condensed and collected, water produced by fuel cells if they're part of the power system. The same basic approach used on the International Space Station, where the water recovery system recycles approximately 93% of water consumed by the crew. 93% sounds excellent, but it means that 7% of water consumed is lost from the closed loop every cycle. On the ISS, that loss is made up by resupply missions that deliver fresh water from Earth roughly every few months. On Mars, there is no resupply. That 7% has to come from somewhere, either from supplemental extraction of local ice, which has all the challenges described above, or from an even more efficient recycling system that loses less per cycle, which requires more complex, more failure-prone technology. The word failure-prone is doing a lot of work in that sentence, and it deserves to be unpacked. Every life support system on a Mars habitat is a closed-loop system operating in an extremely hostile environment, running continuously for months or years, without the possibility of replacement parts being delivered on short notice or expert technicians being flown in to perform repairs. The International Space Station has experienced multiple life support system failures over its decades of operation: carbon dioxide scrubber malfunctions, water recovery system pump failures, oxygen generation system problems. Every one of those failures was manageable because the ISS is in low Earth orbit 8 or 9 hours from Earth by Soyuz capsule, and because Earth-based engineering teams can analyze the problem, devise a solution, and communicate it to the crew in real time. The failure of a critical life support component on Mars is a categorically different situation. If the water recovery system's primary pump fails in month 8 of the surface mission, the crew cannot wait for a replacement part to be launched from Earth. The next launch window to Mars is 26 months away. They cannot receive real-time troubleshooting guidance. The communication delay means a question sent to Earth takes up to 24 minutes to arrive, and the answer takes another up to 24 minutes to return. They have to solve the problem themselves with the spare parts they brought, the tools they have, and the knowledge and skills of the crew members present. This places an extraordinary premium on system redundancy, on crew technical training, on spare parts inventory, and on the design philosophy of the habitat itself. Every critical system needs backup systems. Every backup system needs its own backup. The habitat needs to be designed so that any component can be accessed, disassembled, repaired, and reassembled by a crew member in a pressure suit if necessary, and all of that redundancy and all of those spare parts add mass, which adds cost, which creates pressure to reduce redundancy, to bring the mission within budget, which increases risk. This tension between the redundancy required for safety and the mass constraints imposed by launch economics is one of the most persistent and genuinely difficult problems in Mars mission planning. Let's talk about air, because the atmosphere inside your Mars habitat is as engineered as everything else, and maintaining it requires active, continuous, uninterrupted effort by systems that cannot be allowed to fail. The Martian atmosphere is 95% carbon dioxide. It is at roughly 600 pascals of pressure, less than 1% of Earth's atmospheric pressure at sea level. You cannot breathe it. You cannot step outside without a full pressure suit. The atmosphere inside your habitat is something your life support systems create from scratch and maintain continuously, a breathable mixture of nitrogen and oxygen at a pressure your body can tolerate, scrubbed of carbon dioxide as fast as you and your crewmates exhale it. Carbon dioxide removal is not a background process you can pause or slow down. A resting adult exhales roughly 200 milliliters of carbon dioxide per minute. At work or during exercise, that rate increases substantially. Carbon dioxide begins to cause noticeable symptoms: headache, elevated heart rate, difficulty concentrating at concentrations above roughly 1% of the atmospheric mixture. At concentrations above 3 to 4%, cognitive impairment becomes severe and rapid. At concentrations above 8 to 10%, loss of consciousness and death follow within minutes. The carbon dioxide removal system on a Mars habitat needs to operate continuously, reliably, and at sufficient capacity to keep CO2 below dangerous levels no matter what the crew is doing. On the ISS, this is accomplished primarily by a system called the Carbon Dioxide Removal Assembly, which uses a solid amine sorbent to capture CO2 from the cabin air and then regenerates the sorbent by exposing it to vacuum, releasing the captured CO2 overboard. The ISS has backup systems, and the ISS has Earth-based support, and the ISS has still experienced CO2 scrubber malfunctions that required emergency responses. A Mars habitat will need its own CO2 removal strategy, one that may leverage the Martian atmosphere itself in some configurations, given that the CO2-rich Martian air could theoretically be processed to extract oxygen through systems like the MOXIE experiment carried by the Perseverance rover, which demonstrated small-scale oxygen production from Martian atmospheric CO2 in 2021. MOXIE's first successful production run generated about 5 grams of oxygen, enough for roughly 10 minutes of breathing for one person. Scaled up dramatically, this technology could be a genuine asset. At MOXIE's demonstrated scale, it is a proof of concept, not a survival system. Oxygen generation and carbon dioxide removal are connected loops in a life support system that also includes thermal control, managing the temperature inside the habitat against a Martian environment that can swing from -70 degrees to +20 degrees Celsius across a single day-night cycle, and that conducts heat away from any structure it touches with brutal efficiency through conduction into the cold Martian regolith. The habitat needs to be insulated, heated, and thermally regulated as carefully as it needs to be pressurized. And then there's power. Because none of this works without power, the water recycling system needs power. The carbon dioxide scrubbers need power. The oxygen generation system needs power. The habitat lighting needs power. The heating systems need power. The communication systems need power. The scientific instruments need power. The EVA suit recharging systems need power. The food production systems need power. How much power? Estimates for a minimal Mars surface habitat supporting a crew of 4 suggest a continuous requirement of somewhere between 40 and 100 kilowatts, depending on the mission architecture and what activities the crew is conducting. For comparison, the International Space Station generates roughly 80 to 90 kilowatts from its extensive solar panel arrays, and the ISS is in low Earth orbit, where solar irradiance is roughly 1,360 watts per square meter. At Mars, the Sun is farther away. Solar irradiance at Mars averages roughly 590 watts per square meter, about 43% of what it is at Earth. That means solar panels on Mars generate less power per unit area than the same panels would in Earth orbit, and Mars has global dust storms. We talked about dust storms in Part 2, the way they can reduce sunlight reaching the surface by 99% for weeks or months at a time. Now let's think about what that means for a solar-powered Mars habitat. In November 2018, NASA's Opportunity rover, which had been operating on Mars for nearly 15 years, fell silent as a global dust storm reduced sunlight to levels that could no longer maintain the rover's battery charge. Mission controllers waited months for the storm to clear, hoping the rover's solar panels would be cleaned by wind and its batteries would recharge. They never did. Opportunity, one of the most successful planetary science missions in history, died in a dust storm. Opportunity was a rover with a relatively small power budget. A human habitat requiring 40 to 100 kilowatts of continuous power would face an incomparably more severe challenge during a dust storm that lasted weeks. Even with battery storage to bridge short gaps in solar generation, a prolonged dust event would represent an existential threat to a solely solar-powered habitat. This is why most serious Mars mission architectures, including those being developed by NASA and analyzed by independent research teams, incorporate nuclear power as either the primary or the backup power source. Specifically, small fission reactors, systems like NASA's Killer Power project, which successfully demonstrated a small fission reactor system in ground testing in 2018, capable of generating up to 10 kilowatts continuously from a unit small enough and light enough to be launched to Mars, multiple kilopower units, or their successors, providing reliable, dust storm-independent, day-night continuous power generation would address the power vulnerability that makes a purely solar approach to Mars surface power inadequate for a human mission. But nuclear systems add their own complexities, regulatory, logistical, and operational, and they need to be deployed, positioned, and activated on Mars before the crew arrives, which requires either autonomous robotic systems or a prior crewed mission to set up the infrastructure. Food is the final major consumable we need to address, and it connects all the other systems in ways that make it one of the most interesting engineering and biological challenges of the entire mission. The caloric requirement for a physically active Mars crew member, someone conducting EVAs, performing habitat maintenance, running experiments, and managing the physical demands of life in a novel environment, is substantial. Estimates typically range from 2,400 to 3,200 calories per day per person, depending on body size, activity level, and the specific tasks being performed. For a crew of 4 over a year, that represents somewhere between 3.5 and 4.7 million calories of food energy that needs to be available. Bringing all of that food from Earth as pre-packaged provisions is theoretically possible, but practically problematic for reasons beyond just mass. Nutritional degradation is a serious concern. Vitamins, particularly vitamin C and certain B vitamins, degrade over time even in carefully packaged food, and the transit time to Mars plus the surface mission duration means that some pre-packaged provisions will have been in storage for 2 years or more by the time they're consumed. Studies of ISS food supply have shown measurable vitamin content decreases in provisions over extended storage periods, contributing to the nutritional deficiencies we discussed in the context of crew health. Growing food on Mars in a controlled hydroponic or aeroponic environment inside the habitat offers a partial solution. Fresh-grown vegetables and leafy greens would provide vitamins that degrade in packaged provisions, offer psychological benefits from the act of tending living plants in an otherwise completely artificial environment, and reduce the mass of food that needs to be launched from Earth. NASA's Veggie experiment on the ISS has successfully grown several crops of lettuce, mustard greens, and other vegetables in microgravity, demonstrating that plant growth in spaceflight environments is achievable. But hydroponic food production requires water, nutrients, lighting energy, growing area, and crew time to maintain. The crops that grow most efficiently, lettuce, spinach, radishes, are high in water content and vitamins but relatively low in calories, growing enough calorie-dense staple crops, potatoes, wheat, soybeans, to meaningfully supplement a crew's caloric intake in the growing area realistically available in a Mars habitat would be an extraordinary challenge. The famous calculation from the film The Martian, one character growing enough potatoes in a habitat the size of a tennis court to survive for years, is inspirational fiction, not practical engineering guidance. What emerges from all of this, from the water recycling and the CO2 scrubbing and the power generation and the food production and the thermal management, is a picture of a human Mars habitat as an extraordinarily complex, tightly interdependent system of systems, each one of which must function reliably for a full year in a profoundly hostile environment, and any one of which, if it fails catastrophically and cannot be repaired with on-hand resources, has the potential to end the mission or end the lives of the people depending on it. This is not a reason to give up. The engineers working on these problems are among the best in the world, and the progress being made on closed-loop life support, in-situ resource utilization, and compact nuclear power is genuinely impressive. The path to a Mars mission that can succeed on these technical terms is visible, even if it is long and the hard work is still mostly ahead of us. But it is a reason to be clear-eyed about where we are right now. Every one of the systems described in this part is either still in development, only proven at small scale, or dependent on technology that has not yet been demonstrated in the actual Mars environment. The margin between a mission that sustains its crew for a year and a mission that doesn't is not wide. It is not comfortable. It is maintained by redundancy, by preparation, by the skill and calm judgment of the crew, and by a measure of good fortune that no mission planner likes to include in their calculations, but that is, honestly, part of every mission that has ever flown. If you are still watching, it means that channel was made exactly for you. Don't forget to subscribe and give this video a thumbs up. You will be part of a community that explores the cosmos together. It starts with a sound, not an explosion, not a siren, just a sound, a faint high-pitched hiss that one of the crew members notices during what should be a routine morning check of the habitat's pressure sensors. It's subtle enough that for a moment they wonder if they imagined it. They didn't. The habitat pressure is dropping, slowly but measurably, 0.3 pascals per minute. In the context of a habitat maintained at roughly 100,000 pascals of internal pressure, about the same as Earth's atmosphere at sea level, that rate sounds almost trivial. It isn't. A sustained leak at that rate, unaddressed, will drop the habitat to dangerous pressure levels within hours. And on Mars, dangerous pressure levels inside the habitat means the same thing as the pressure outside, 600 pascals of near vacuum that no human being can survive unprotected for more than a few seconds. This is not a catastrophic scenario. It is not a meteor strike punching through the habitat wall. It is not a sudden explosive decompression. It is a slow leak. The kind of thing that habitat engineers design for, that EVA protocols prepare for, that crew training addresses in detail. It is in the taxonomy of Mars mission emergencies, a manageable problem. But watch what happens when a manageable problem unfolds in the Martian environment. The crew has been on Mars for 218 days. They are past the halfway point of their planned surface stay, and they are carrying the accumulated physiological burden of everything we've discussed over the previous 6 parts of this script. Their bone density is measurably lower than it was on departure from Earth. Their muscle mass has declined despite the exercise regimen. Their cardiovascular systems have adapted to the reduced demands of Martian gravity in ways that have quietly reduced their peak aerobic capacity. At least 2 of the 4 crew members have experienced episodes of elevated intracranial pressure affecting their vision. They are also tired in a way that is difficult to fully convey to someone who has never experienced it. Not the tiredness of a long day or a difficult week, but the deep, chronic, accumulated fatigue of more than 300 days of unbroken stress, disrupted sleep, monotonous environment, and the constant low-level cognitive load of living in a place where a mistake can be fatal. Studies of long-duration mission crews consistently show that cognitive performance, reaction time, and decision-making quality degrade over the course of a mission in ways that are not fully offset by rest, and that the second half of a mission tends to be harder cognitively and emotionally than the first half. So the crew that hears that hiss on day 218 is not the crew that landed. They are competent, trained and professional, but they are operating with smaller reserves than they had on arrival. And that matters, because what comes next is going to demand a great deal from those reserves. The first task is locating the leak. This sounds straightforward. It is not. The habitat is not a simple structure. It is a complex assembly of interconnected modules, living quarters, laboratory space, airlock, life support systems room, food production area, connected by pressurized tunnels and containing thousands of meters of tubing, wiring, and structural joints. Any of these connections is a potential leak point. The habitat's pressure monitoring system can localize the leak to a general area. In this scenario, let's say it's somewhere in or near the airlock module, but pinpointing the exact location requires physical inspection. 2 crew members suit up for an internal inspection of the airlock module. Suiting up takes approximately 30 minutes, donning the pressure suit, checking the seals, running the pre-breathe protocol to reduce the risk of decompression sickness as the suit's atmosphere differs from the habitat's. During those 30 minutes, the habitat pressure has continued to drop. It is now at 99,300 pascals, still safe, but the trend line is visible, and the crew members who are not suiting up are watching the sensors with the particular quality of attention that people give to numbers that are moving in the wrong direction. The two crew members who suit up enter the airlock module and begin the inspection. They are looking for a breach in the module wall, a failed seal at a connection point, a crack in a viewport, a compromised gasket around a hatch. They are doing this in full EVA suits, which reduces their dexterity significantly. The gloves that protect their hands from the Martian environment also make fine manipulation difficult. They are doing it in a confined space, and they are doing it while the habitat around them continues to lose pressure at a slow but steady rate. After 45 minutes of inspection, they find it. A hairline crack in the composite material around one of the airlock's secondary viewport frames. The crack is perhaps 4 centimeters long and less than a millimeter wide, barely visible to the naked eye, and only found because one of the crew members thought to use an ultrasonic leak detector rather than relying on visual inspection alone. This is, again, a manageable problem. The habitat carries emergency sealant compounds specifically for this purpose, materials that can be applied over a crack or joint failure to restore pressure integrity temporarily, while a more permanent repair is planned. The crew member applies the sealant, the leak stops, the habitat pressure stabilizes. It has been 1 hour and 40 minutes since the hiss was first noticed. The habitat pressure dropped to 98,600 pascals before the leak was sealed, a reduction of about 1.4% from nominal. The crew is tired. They've been operating under elevated stress for nearly 2 hours, but the immediate crisis is resolved. Except now the second problem is visible. During the inspection of the airlock module, one of the crew members noticed something else. The primary EVA suit, the one designated for the crew commander, and the most recently used suit for a surface excursion 3 days ago, shows an anomalous reading on its pressure integrity sensor. The suit's diagnostic system is flagging a potential seal degradation at the left wrist joint. The reading is ambiguous. It could be a sensor malfunction, or it could be an actual developing seal problem. But the crew commander's next scheduled EVA is in 36 hours to collect a soil sample from a site 2.3 kilometers from the habitat that the science team has been waiting on for 2 weeks. If the wrist seal is actually degrading, using that suit for an EVA is potentially fatal. If the sensor is malfunctioning and the seal is fine, cancelling the EVA means delaying a scientific objective that required months of planning and represents a significant portion of the mission's scientific return. To determine which it is, the crew needs to perform a full pressure test of the suit, a process that takes several hours and requires setting up a test rig that uses equipment from the life support systems room. The same life support systems room that 2 crew members spent the last hour and 40 minutes partially disassembled during the airlock inspection, and that needs to be checked and recertified before the test rig can be set up safely. The commander contacts Earth to report the situation and request guidance. The message takes up to 24 minutes to arrive at mission control. The response takes another up to 24 minutes to return. During that waiting period, up to 48 minutes of one-way communication delay before they can receive any guidance. The crew has to decide whether to proceed with the suit test preparation or wait for Earth's input. They proceed because waiting is not neutral. Every hour of delay in resolving the suit question reduces the planning window for the EVA. Mission Control's response, when it arrives, is thorough and helpful. It confirms the test procedure, identifies two components in the suit's wrist assembly that have shown similar sensor anomalies in ground testing and turned out to be minor calibration drift rather than actual seal problems, and suggests a specific diagnostic check that can determine within 30 minutes whether the seal is compromised or the sensor is at fault. The diagnostic check is performed. The seal is fine, the sensor is drifting, the EVIA is confirmed for 36 hours from now. 48 minutes of communication round trip, 2 hours of diagnostic work, the earlier 1 hour and 40 minutes of leak response. The crew has now been managing back-to-back problems for the better part of a shift, and the day is not over. Now consider adding one more variable. Because this is Mars, and on Mars the variables don't wait politely for you to finish dealing with the last one. The dust sensor mounted on the habitat's exterior mast, which the crew checks as part of the standard end-of-shift systems review, shows elevated atmospheric particle counts. Not a global storm, nothing like the event that killed Opportunity. A regional dust event, the kind that forms and dissipates in days to weeks, reducing solar irradiance by 30 to 50% in the affected area. The habitat's solar panels, which supplement the nuclear power system and handle peak loads during high-demand periods, are already showing reduced output. Not critical, the nuclear system handles the baseline load, but the buffer that solar provides for peak demands like suit testing, water processing cycles, and the food production lighting array is significantly reduced. Mission control is informed. The response, 48 minutes later, recommends postponing non-essential high-power activities for the duration of the dust event. The EVIA in 36 hours is still viable. The suit systems run on their own battery power, and the airlock cycling uses a manageable amount of habitat energy. But the science laboratory's mass spectrometer, which has been running a continuous analysis sequence for the past week, needs to be powered down to conserve energy. 3 crew members need to be briefed, the instrument state needs to be carefully saved, and the analysis will need to be restarted when full power is available, adding days to a scientific timeline that is already constrained by the mission's fixed end date. The crew is now managing the aftermath of a habitat pressure leak, a suit sensor anomaly, and a dust event power restriction simultaneously, all while maintaining the basic daily requirements of the mission, the exercise regimen that cannot be skipped without accelerating bone and muscle loss, the food preparation, the sleep schedule that is already compromised by stress, and the routine monitoring of all the other systems that keep them alive. This is a bad day on Mars. Not a catastrophic one. Nobody was injured. The habitat is intact. The suit is confirmed safe for the upcoming EVA. The power situation is manageable. In the taxonomy of Mars mission incidents, what I've described is a medium severity day, worse than average, better than the genuinely dangerous scenarios mission planners stay up at night thinking about. But look at what it required. It required the crew to perform physically demanding, technically precise work in a high-stress environment while wearing equipment that reduces dexterity and increases fatigue. It required clear communication and sound decision-making from people who are more than 200 days into a mission that has been eroding their cognitive reserves since they left Earth. It required the ability to triage competing problems, manage uncertainty about equipment status, work within the constraints of a communication delay that makes real-time expert guidance impossible, and do all of this while maintaining the discipline to not skip the tasks, the exercise, the monitoring, the routine maintenance that keep the bigger systems stable. And it required a body that was up to the task, a cardiovascular system that could handle the physical demands of suited work, bones strong enough to manage the unexpected physical loads of working in an EVA suit in a cramped module, a visual system that wasn't compromised enough by SANS to make precision work difficult. a brain that was still performing at sufficient cognitive level to manage the decision tree of a multi-problem emergency without making a judgment error that cascades into something worse. The scenario I've described assumes the crew gets all of this right, and trained, professional astronauts, supported by excellent mission architecture and ground teams, probably would get most of it right most of the time. The human capacity for performance under pressure, particularly among people who have been selected and trained for exactly these conditions, is genuinely remarkable. But performance under pressure is not infinite. It degrades with time, with fatigue accumulation, with physiological impairment. The probability of a critical error, not a catastrophic, unrecoverable error necessarily, but an error that makes a bad situation worse, increases as the mission goes on and the crew's physical and cognitive reserves are drawn down. Space medicine researchers talk about something called the third quarter phenomenon, a documented pattern in isolated, confined, long-duration mission crews where performance and psychological stability tend to dip in the third quarter of the mission. The initial novelty has worn off. The end is visible but not yet close. Fatigue is well established. Group dynamics have had time to develop whatever tensions they're going to develop. On an Antarctic winter-over mission, this phase typically shows increased interpersonal conflict, reduced motivation, and more errors in routine tasks. A Mars surface mission in its third quarter would be somewhere around days 200 to 270 of the surface stay, which is, incidentally, roughly when systems that have been running continuously for the longest time start showing the wear patterns that cause the kind of subtle failures I described at the beginning of this part. The third quarter phenomenon in human performance and the third quarter wear patterns in mechanical systems arrive at approximately the same time. There is a concept in engineering called a single point of failure, a component within a system whose failure will cause the entire system to fail because there is no redundancy at that node. Good engineering practice tries to eliminate single points of failure by building in backups, redundant pathways, and graceful degradation modes. But in a Mars habitat operating under mass constraints, eliminating every single point of failure is not entirely possible. There will be nodes in the system where a failure is severe enough, and the backup capability limited enough that the outcome becomes critical. The human crew member is paradoxically both the most robust and the most fragile element in this system. Robust, because human beings are adaptable in ways that no engineered system fully matches. We can improvise, we can learn on the fly, we can find solutions to problems that weren't anticipated in the design. Fragile, because a human being requires constant maintenance of 4 kilograms of consumables per day, operates a physiological system that is being progressively impaired by the environment, and is operating at the end of a decision chain where every error has consequences that cannot be easily reversed. The crew is simultaneously the solution to every problem on Mars, and the problem that the life support systems, the habitat engineering, and the mission architecture are all trying to solve. Let's talk about distance the way it actually feels. Not as a number in an astronomy textbook, not as a travel time calculated at the speed of light, as a lived, physical, psychological reality that no human being in the history of our species has ever experienced, and that no amount of training, preparation, or mental toughness can fully neutralize. At its closest approach to Earth, Mars is about 54 million kilometers away. At its farthest, it is over 400 million kilometers away. The average distance across a typical mission is somewhere around 225 million kilometers. These numbers are so large that they stop meaning anything to the human brain almost immediately. We don't have an intuitive sense of what 200 million kilometers feels like. So let me give it to you a different way. If you were standing in your Mars habitat right now, day 218, after the leak and the suit sensor and the dust event, and something went badly wrong, not a slow leak, not an ambiguous sensor reading, something unambiguous, a crew member collapsed, a critical system failed in a way that your spare parts inventory cannot fix, a medical emergency that requires equipment or expertise you don't have on the surface, you call Earth, you send the most urgent distress signal you can compose, and then you wait, at least 3 minutes, possibly up to 24 minutes, for the signal to arrive, then the same time again for the response. No matter how skilled the team on Earth, no matter how senior the flight surgeon on duty, no matter how much anyone on the planet cares about what is happening to you, the physics of the distance means that they cannot be present with you in your emergency. They can only speak to you across a gap of minutes, offering guidance that arrives after the moment has already passed. And even if every conversation went perfectly, even if every piece of advice from Earth was exactly right and delivered in time to be useful, there is no physical help coming. No rescue mission launches in response to a crisis on Mars. The orbital mechanics don't allow it. The preparation time doesn't allow it. The nearest human being to your crew is the crew itself, 8 or 9 months of travel time away on a planet that is entirely uninvested in your survival. Humans are not built for this. That is not a criticism. It is a biological and evolutionary fact. The human nervous system, the human psychological architecture, the entire suite of cognitive and emotional tools that our species developed over hundreds of thousands of years, evolved in an environment where the fundamental social safety net, the knowledge that other people could reach you, help you, rescue you, was always theoretically present. Even in the most isolated human environments in history, there was always the possibility, however remote, that someone could come. Hunters stranded in a blizzard, sailors lost at sea, explorers in unmapped territory. The help might not arrive in time, but it could arrive. The universe was not structurally preventing it. On Mars, the universe is structurally preventing it. Not through bad luck or inadequate planning or insufficient resources, through the simple, unalterable fact of distance. This is a new kind of isolation for the human mind to process, and it processes it in ways that are not always predictable, not always manageable, and not always visible until they've already affected the decisions being made. Space psychologists have a term for the psychological impact of communication delays and physical unreachability. They call it Earth out of view phenomenon, and it has been studied in analog environments, Antarctic research stations, submarine deployments, isolated habitat simulations with consistent findings. People cope with remote isolation through a psychological process called Earth anchoring, maintaining a felt sense of connection to home, family, and the broader human community through communication, through familiar objects and rituals, through the knowledge that Earth is present and accessible, even if far away. On Mars, Earth anchoring is actively undermined by the communication delay. A conversation with a loved one at home is not a conversation. It is an exchange of recorded messages. Send a thought, wait up to 48 minutes for a response, send a follow-up, wait again. The spontaneous, real-time quality of human connection, the thing that actually makes a phone call with someone you love feel like connection rather than information exchange, is gone. What remains is something more like correspondence, letters with a very fast postal service by historical standards, but letters nonetheless. The crews who have spent the most time in the most isolated analog environments on Earth have provided some of the most detailed accounts of what long-term isolation from real-time communication does to the human mind, and the picture they paint is nuanced and worth understanding. The first phase of a long-duration isolated mission is typically characterized by heightened engagement. The novelty of the environment, the clarity of purpose, the energy of being part of something significant. People in this phase often describe feeling more focused and motivated than they do in ordinary life. The mission feels real and immediate and important, and the isolation feels manageable because the novelty hasn't worn off yet. The second phase, which typically begins somewhere between 1 and 3 months, depending on the mission and the individual, is characterized by adaptation, a settling into routine, a reduction in novelty-driven engagement, and the beginning of the psychological work of genuinely processing the isolation. This is when homesickness becomes most acute, when interpersonal tensions in the crew begin to emerge, and when the emotional distance from Earth starts to feel like a physical weight rather than just an abstract fact. The third phase, the one that corresponds to the second half of the mission, is the most variable. For some individuals and some crews, it is characterized by a kind of adaptation and acceptance that actually produces the deepest and most meaningful work of the mission. For others, it is characterized by increasing psychological strain, cognitive dulling, emotional flatness, and the kind of motivational erosion that space medicine researchers describe as behavioral health deterioration. The difference between these outcomes depends on crew composition, leadership quality, mission support from Earth, and individual psychological factors that are difficult to fully screen for in advance. What does behavioral health deterioration actually look like in practice? It doesn't look like a breakdown. It doesn't look like a dramatic crisis. It looks like small things. A crew member who is consistently slower to respond to communication from mission control. Another who has become uncharacteristically quiet in group planning sessions. A third who has started making minor errors in routine procedures that they never made in the first half of the mission. Not dangerous errors, not yet, but the kind of small mistakes that indicate a reduction in the careful, deliberate attention that safe operations require. None of these things are individually alarming. All of them together, in a crew that is operating in an environment where small mistakes can cascade into large ones, represent a genuine operational risk that is difficult to manage from Earth and difficult for the crew members themselves to fully perceive, because the same cognitive dulling that causes the errors also reduces the metacognitive awareness needed to notice that something is wrong. This is one of the reasons that behavioral health monitoring is taken so seriously in long-duration spaceflight planning. On the ISS, psychological support includes regular private communication sessions with a psychologist on Earth, family conferences, surprise care packages with comfort items, and a dedicated Earth-based team that monitors crew communication patterns and raises flags when changes suggest emerging stress or interpersonal conflict. On Mars, the communication delay makes all of these interventions less effective. A psychological support session where each exchange takes up to 48 minutes round trip is a fundamentally different experience from a real-time video call with a counselor. The Earth-based team can still monitor, still provide guidance, still send care packages in advance. But the immediacy that makes psychological intervention most effective is compromised by the same physics that limits everything else. Now add to this the specific psychological weight of medical risk. On Earth, or even on the ISS, a crew member who experiences a serious medical emergency has access to a system, emergency services, hospital facilities, surgical capability, specialist expertise. The system is imperfect and outcomes are not guaranteed, but the system is there. On Mars, the medical system is whatever the crew brought with them and whatever skills the crew members have. Mars mission crews will include at least one person with advanced medical training, likely a physician or a flight surgeon equivalent with surgical capability and broad internal medicine knowledge. The medical kit will be extensive by spaceflight standards, including diagnostic equipment, surgical supplies, pharmaceuticals covering a wide range of conditions, and telemedicine capability that allows Earth-based specialists to guide procedures in real time across the communication delay. But the medical reality of a Mars mission is this. If a crew member develops acute appendicitis on day 150, the crew surgeon will perform the appendectomy in the habitat's medical bay, guided by a surgical team on Earth, whose most recent communication arrived 18 minutes ago. The procedure is achievable. Appendectomies have been performed in field conditions since the 19th century, and laparoscopic techniques reduce the complexity significantly. But it will be performed by someone who is, themselves, physiologically impaired by months of Martian conditions, in a facility that is far below hospital standard, with no option to call for backup if something goes wrong. If a crew member has a stroke, which becomes more likely as cardiovascular deconditioning progresses and as the blood pressure effects of fluid shifts in reduced gravity alter cerebrovascular dynamics, the treatment options are limited. Stroke management requires imaging capability, clot-dissolving medications that need to be administered within a very narrow time window, and in many cases, surgical or catheter-based intervention that is simply not available on the Martian surface. A stroke that would be manageable at a hospital on Earth could be permanently disabling or fatal on Mars depending on its severity and the precise location of the affected tissue, and if a crew member dies, the remaining crew has to continue the mission. They have to conduct the burial or the body preservation. They have to redistribute the deceased crew members' responsibilities across a team that is now one person smaller. They have to process the grief, real, acute, profound grief, while continuing to perform the precision work that keeps the rest of them alive. The psychological literature on how isolated crews respond to the death of a team member is limited because it hasn't happened in space yet. The Antarctic literature, the submarine literature, and the wartime isolated unit literature all suggest that the impact is deep and lasting, and that it affects operational performance in ways that are difficult to fully anticipate or mitigate. There is a concept in risk assessment called dread risk, a category of risk that people perceive as particularly frightening, not necessarily because it is statistically likely, but because it is uncontrollable, catastrophic, and has no possibility of rescue or mitigation once it begins. Flying in a commercial aircraft, statistically, is far safer than driving a car, but far more people are afraid of flying than of driving because a plane crash feels uncontrollable in a way that driving does not. Dread risks produce a specific kind of chronic background anxiety in people who are exposed to them, a persistent, low-level awareness of catastrophic possibility that is cognitively taxing to manage over long periods. A Mars mission is saturated with dread risks. The habitat breach that can depressurize before you can respond. The EVA suit failure that gives you minutes of survival time in the open Martian environment. The life support cascade failure that consumes your oxygen reserve faster than you can address the fault. None of these things are likely on any given day, but they are possible every day. And unlike the dread risks of ordinary life, car accidents, plane crashes, the people on a Mars mission are aware of them at a technical level of detail that most people never need to understand. They know exactly how a suit seal fails. They know exactly how fast the habitat pressure drops in a catastrophic breach. They know the numbers because the numbers are part of their training. Managing that knowledge, holding it in a part of the mind that stays operational and careful rather than becoming paralyzed, is a form of psychological work that is never finished during the mission. It is part of the cognitive load that accumulates across the months, alongside the physical impairment and the accumulated fatigue and the loneliness of knowing that the nearest city is a planet away. And yet, and this matters, and it would be dishonest not to say it, people have demonstrated an extraordinary capacity to endure this kind of pressure and emerge from it not just intact, but transformed. The men and women who have wintered over in Antarctica for 7 or 8 months in complete isolation have described the experience as among the most clarifying of their lives. Cosmonauts who have completed year-long missions aboard the ISS have returned to Earth, changed in ways they describe as profound and positive, a deepened sense of perspective, a more deliberate relationship with time and attention, a clarity about what actually matters that comes from having been in a place where the irrelevance of most ordinary concerns was undeniable. Scott Kelly, who spent 340 consecutive days aboard the International Space Station, described the final months of his mission as a kind of strange grace, a period of profound difficulty and profound meaning existing simultaneously, the isolation and the hardship made bearable by the clarity of purpose and the magnitude of what he was part of. He came back changed. He came back with altered DNA expression, altered microbiome composition, altered physiology that took months to partially recover. He came back having lost bone density and muscle mass and having experienced vision changes from SANS that required corrective lenses. He came back diminished in some measurable biological ways, and he came back saying he would do it again. That tension between the genuine, documented, non-trivial damage that long-duration space flight causes to the human body and mind, and the genuine human capacity to endure, adapt, and find meaning in the most extreme conditions, is the tension at the heart of the Mars question. It is why the answer to why you wouldn't survive 1 year on Mars is not a simple no. It is a complex, qualified, scientifically grounded answer that acknowledges both the scale of what we're asking human bodies and minds to do and the scale of what human beings have proven capable of when the mission is real and the stakes are ultimate. The question is not whether anyone will ever go to Mars. The question is whether we will go ready, with the medical knowledge, the engineering systems, the psychological support infrastructure, and the honest understanding of the risks that the mission demands. Whether the first humans to stand on that red surface will have everything they need to survive, not just the launch vehicle and the habitat, the full picture, the whole truth of what Mars does to a human being across a year of exposure. Let's do the accounting, not the budget kind, the biological kind, the kind where you add up everything Mars has taken from you across 365 days and look at the total honestly, without softening it, without rushing to the reassuring part. Because before we can talk about what it means to come home, we need to understand what you are at the end of the year, what the mission has made of the body and mind that arrived on that surface full of training and purpose, and the physical condition that years of preparation produced. Start at the top. Your brain is not the same brain that landed. We covered the structural changes earlier, the upward fluid shift that increases intracranial pressure, the white matter changes visible in imaging studies, the flattening of the globe at the back of the eye that degrades visual acuity and sometimes causes permanent vision loss. These are the changes we can see with the tools we have. But there is a broader cognitive picture that emerges from the accumulated data of long-duration spaceflight, and it is worth laying out in full. Across the course of a year-long mission, the research consistently shows measurable changes in several domains of cognitive performance. Processing speed, the raw quickness of mental response, declines. Working memory, the mental workspace you use to hold and manipulate information in real time, shows impairment. spatial reasoning, the ability to mentally rotate and navigate through three-dimensional environments, which is precisely the kind of thinking you need most when operating in a complex technical habitat on an alien planet, deteriorates. Sustained attention, the ability to remain focused on a demanding task for extended periods without degradation in accuracy, becomes harder to maintain. These are not dramatic changes. The crew is not cognitively incapacitated. They are still performing, still making decisions, still executing procedures, but the margins are narrower. The cognitive reserve, the buffer between baseline performance and the threshold below which errors become likely, has been reduced. And in an environment where errors carry potentially lethal consequences, narrower margins matter enormously. Now add the fact that the return transit is 9 months of additional space flight, 9 more months of radiation exposure, 9 more months of microgravity, 9 more months of the physiological processes that have been ongoing since departure from Earth. The cognitive impairments that have accumulated across the year on the surface do not pause during the journey home. They continue. Your skeleton has been quietly failing for 12 months. Bone density loss in microgravity and reduced gravity environments occurs at a rate of approximately 1 to 1.5% per month in the most affected regions, the lower spine, the hip, the femur. At 1% per month over 12 months, you have lost roughly 12% of your bone density in those load-bearing structures. At 1.5%, the loss approaches 18%. To put that in a human context, an 18% reduction in hip bone density places you in a range that, in a 70-year-old patient on Earth, would be classified as significant osteoporosis and would prompt immediate clinical intervention. You are not 70, you are a trained astronaut in the prime of life, but your skeleton, in the regions that matter most for weight-bearing activity on a full-gravity planet, has the structural integrity of someone who is. The countermeasures, the resistance exercise protocols, the bone-stimulating medications that future long-duration missions will almost certainly employ, can slow this process. Current data from the ISS, where exercise countermeasures are well established, suggests loss rates can be reduced to perhaps 0.5% to 1% per month with aggressive intervention. That's better. It is not solved. 12 months at even 0.5% means a 6% reduction in bone density in the most critical regions. In a person who is about to re-enter an environment with full Earth gravity, that loss carries a very specific risk. Fracture, the scenario that concerns space medicine specialists, most is not a dramatic break from a fall. It is a stress fracture, the kind that occurs not from a single traumatic event, but from the cumulative load of simply walking, standing, carrying your own weight in a gravitational field that is 2.5 times stronger than the one your skeleton has been adapting to for a year. The returning crew member steps off the return vehicle, takes their first steps on Earth, and the femur, or the vertebral body, or the hip, fractures under a load it used to handle without noticing. This is not a hypothetical fear. It is a documented risk that space medicine teams plan for concretely. Return from long-duration spaceflight involves a carefully managed readaptation period in which the crew does not simply walk out of the spacecraft. They are carried, they are supported. Their first contact with full gravity is mediated by trained recovery teams whose job is to make sure the body's reintroduction to its home environment doesn't destroy the very structures it needs to navigate that environment. Your muscles have lost mass continuously since you landed, despite exercise, despite protein intake, despite every intervention available. Muscle atrophy in reduced gravity is driven by the fundamental reduction in mechanical demand. The body stops maintaining tissue it has determined it doesn't need to use. And in a gravity environment 1/3 of Earth's, it doesn't need to use very much. The lower body is most affected. because the lower body is specifically designed to handle the loads of Earth gravity, and those loads simply don't exist on Mars. The postural muscles of the back and core, which work constantly on Earth just to keep you upright, experience a similar reduction in demand. After 12 months, the estimates for lower body muscle mass loss, even with countermeasures, are in the range of 10 to 20%, depending on the individual and the rigor of the exercise protocol. That is not a number that sounds dangerous until you consider what it means for function. A 20% reduction in lower body muscle mass means that the simple act of standing up from a seated position, something your neuromuscular system usually handles without conscious thought, now requires deliberate effort and produces fatigue that it didn't before. Walking on a treadmill during the return transit is part of the readaptation protocol precisely because the crew needs to begin rebuilding the neuromuscular patterns for Earth-level locomotion before they arrive. The cardiovascular system has undergone parallel changes. Cardiac muscle, like skeletal muscle, adapts to demand. In reduced gravity, the heart doesn't need to pump blood as forcefully against the pressure gradient that runs from head to foot on Earth, because that gradient is weaker on Mars. The heart adapts. It becomes slightly smaller. Its output capacity decreases. Its efficiency in the specific task of supporting upright bipedal locomotion on a one-gravity planet declines. Returning to Earth gravity means the cardiovascular system is suddenly required to perform at a level it has been quietly downgrading for a year. The most common immediate consequence is orthostatic intolerance, the inability to maintain adequate blood pressure when standing upright, which produces dizziness, lightheadedness, and in significant cases, fainting. Scott Kelly, after 340 days on the ISS, experienced severe orthostatic intolerance upon return. He described the sensation of standing as physically agonizing, his skin hypersensitive to touch, his legs burning under the weight of his own body. He had returned to the planet he was born on, and his body treated it as a hostile environment. Your immune system has been running abnormally for 12 months. The dormant viruses, the herpes viruses that live quietly in your nervous system for your entire adult life, held in check by normal immune surveillance, have been shedding at elevated rates. Epstein-Barr, cytomegalovirus, varicella zoster, not causing full reactivation in most cases, not producing overt illness, but active in ways they shouldn't be, producing a chronic low-level immune burden that contributes to fatigue, to inflammatory processes, and to the generalized sense of being less than fully well that long-duration crew members describe as a persistent background feature of extended missions. The immune system's functional capacity, its ability to mount a full, rapid, effective response to a new pathogen, has been impaired by the combined effects of stress, radiation, and the gut microbiome disruption that months in a sealed, low-diversity environment produces. The gut microbiome, that community of 38 trillion microbial cells that trains and regulates immune function, has been living in an environment with limited dietary diversity, limited microbial inputs from the outside world, and months of exposure to the stresses that suppress microbial community stability. This matters for the return to Earth because Earth is not a sterile environment. Earth is a planet saturated with microbial life, airborne, surface-borne, in the food, in the air, in the soil, in the people who will be hugging the returning crew at the recovery site. A healthy immune system handles this without difficulty. It has been trained across a lifetime of exposure. An immune system that has been running on reduced capacity for a year, with a depleted microbiome and a dysregulated response profile, may handle it less well. The returning crew will be monitored in medical quarantine for a period that serves both the purpose of supporting their physical readaptation and assessing their health status before full reintegration. This is not just a formality. It is a recognition that the body they are returning in is genuinely different from the body they left in, and that its interactions with the home environment need to be managed rather than assumed. Now add the 9 months of return transit to everything described above, because the year on Mars is not where the accumulated damage stops. The return transit is 9 months of microgravity, true microgravity, not the 38% of Mars gravity that at least provides some skeletal and cardiovascular loading, 9 months in which the bone loss, which may have partially stabilized or even slightly reversed on the Martian surface due to the low but real gravity, accelerates again under weightless conditions. 9 months in which the muscles that were slowly rebuilding toward the demands of Earth begin the long decline again. 9 months of radiation, of immune stress, of psychological isolation on a spacecraft that is headed toward a destination that is increasingly large in the window but still months away. The total duration of the mission, from Earth departure to Earth return, is approximately 2 years and 6 months for a baseline Mars surface mission. 2.5 years of continuous physiological impairment, accumulating damage and resource depletion. The person who returns to Earth is not the person who left. In measurable, documented physiological ways, they are not. The studies of identical twins in which one twin flies a long-duration mission, the most famous being the NASA twin study involving Scott and Mark Kelly, have provided some of the most detailed evidence of how profoundly extended spaceflight alters fundamental biology. Across the year of the mission, researchers documented changes in gene expression, telomere length, cognitive performance, microbiome composition, epigenetic markers, and inflammatory profiles. Most of these changes partially or fully reversed after return to Earth over a period of months to years. Some did not fully reverse within the period of the study. The genes that changed expression most significantly were those associated with immune function, DNA repair, and the body's response to hypoxia, low oxygen conditions. The body of the astronaut in space is not just stressed, it is actively rewriting its own operational parameters in response to the environment it is in. It is becoming, in a real molecular sense, a different biological entity. So what does this mean for the actual question we've been building toward across this entire journey? Why you wouldn't survive 1 year on Mars? Let me be precise about the word survive because it matters. If you define survival as biological continuation, heartbeat, brain function, the basic persistence of life, then the odds of survival for a well-prepared crew with good engineering and solid training are not negligible. People have survived over a year in the most comparable environment we have access to, the ISS, without dying. The 6 cosmonauts and astronauts who have completed year-long or near-year-long missions in low Earth orbit returned home damaged but alive. The engineering of life support is achievable. The medicine is manageable for most scenarios. But if you define survival the way it actually matters, as emerging from the experience with a body that still functions at the level required to complete the mission and return safely, with a mind that is still capable of making the decisions that the mission demands, with the physical resilience to re-enter Earth gravity without catastrophic injury, then the picture is significantly more complicated. The year on Mars is not one challenge. It is not 5 challenges or 10 challenges. It is a continuous, simultaneous, multi-system assault on every aspect of human physiology and psychology in an environment that provides no margin for error, no external rescue, and no reprieve. The radiation is happening while the bone is thinning. The bone is thinning while the muscles are atrophying. The muscles are atrophying while the cardiovascular system is deconditioned. The cardiovascular system is deconditioned while the immune system is dysregulated. The immune system is dysregulated while the brain is accumulating fluid pressure changes and white matter alterations, All of it is happening at the same time, every day, for 365 consecutive days. And the human being experiencing all of this is simultaneously responsible for operating a technically complex, life-dependent habitat system, conducting scientific research of historic significance, maintaining functional relationships with 3 or 4 other people in a space smaller than a modest apartment, processing the psychological weight of distance and unreachability and dread risk, and making real-time decisions in emergency scenarios that arrive without warning and cannot wait for Earth's guidance. This is not a case against going to Mars. It is a case for going honestly, for going with the full scientific understanding of what the journey does to a human being, not the version that papers over the harder findings because they are inconvenient for the narrative of inevitability. It is a case for the years of additional research into radiation countermeasures, into pharmacological bone protection, into microbiome preservation, into the psychological architecture of extreme isolation that the mission actually requires before it is ready to fly with human beings on board. The engineers who are designing the habitats and the propulsion systems and the life support are doing extraordinary work. The mission planners who are thinking through the contingency scenarios are doing extraordinary work, but the human body is not an engineering problem with an engineering solution. It is a biological system shaped by 4 billion years of evolution on a specific planet, in a specific gravity well, under a specific magnetic shield, in a specific microbiome environment. Taking it off that planet and putting it on a different one asks it to do something it was not designed to do, and understanding exactly what that costs, in precise biological detail, with honest acknowledgement of the limits of current countermeasures, is not pessimism. It is the foundation of a mission that actually succeeds. Here's the question nobody wants to sit with. We've spent 9 parts building the most honest, scientifically grounded picture we can of what Mars does to a human being, the radiation that chips away at your DNA every single day, the atmospheric pressure so thin it would kill you in seconds without a suit, the perchlorates in the soil that would poison your thyroid if you breathed the dust, the gravity that quietly dismantles your skeleton and your heart and your muscles over months of exposure, the isolation that rewires your psychology in ways that are difficult to detect from the inside and difficult to reverse from the outside, the cumulative, simultaneous, relentless biological cost of being somewhere your body was never designed to be. We laid it all out. We didn't soften it. We didn't rush to the reassuring part. And now I'm going to ask you to hold all of that, every data point, every medical risk, every engineering constraint, and answer this question honestly. Why are we still going, not are we going? We are. That's not seriously in doubt anymore. The trajectory of human spaceflight, the resources being devoted to it, the engineering progress being made, the institutional commitment of multiple space agencies and private companies across multiple countries, points in one direction. Humans will stand on the surface of Mars. The question of whether has effectively been replaced by the question of when and how well prepared. So the real question is the deeper one, the one that sits underneath the engineering and the medicine and the mission planning, the one that the biology and the risk assessments and the mortality statistics don't answer. Why does our species keep reaching toward places that want to kill it? Let's start with the practical argument, because it's real and it deserves to be stated plainly. Earth is one planet, one biosphere, one magnetic shield, one set of tectonic plates, one atmosphere, climate system, one collection of interconnected ecosystems that have been sustaining complex life for hundreds of millions of years, and that we have been stressing in measurable, documented ways for the last 2 centuries. The history of life on this planet is also a history of mass extinction events, 5 of them in the fossil record that we know of, each one resetting the biological clock by destroying the majority of species then alive. The mechanisms that caused those extinctions are not gone. An asteroid large enough to cause a mass extinction event will strike Earth again. Not tomorrow, not in our lifetimes, almost certainly not in our civilization's current chapter, but on geological timescales, the timescales on which planetary history operates. It is a certainty rather than a possibility. The question is not whether Earth will be struck again by something capable of ending complex life. The question is whether, when it happens, there is complex life anywhere else. A species that exists on only one planet is a species whose entire existence depends on the continued habitability of that one planet. Every egg in one basket, every copy of the human story stored in one location, every version of consciousness that we know exists anywhere in the universe concentrated on one pale blue dot in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars. From a pure risk management perspective, becoming a multi-planetary species is not ambition, it is insurance. It is the most basic form of redundancy, the same redundancy that every good engineer builds into critical systems, that every sensible person understands when they back up important files in more than one place. If something happens to Earth, and Earth alone carries humanity, then humanity ends. If Mars carries even a small self-sustaining human presence, then something of us continues. The story doesn't end. That's the practical argument. It's compelling. It's rational. It's the kind of argument that plays well in budget hearings and policy documents and TED Talks. But I don't think it's the real reason. I think the real reason is older than risk management, older than space agencies, older than the scientific method, older possibly than language itself. Something in our species moves toward the horizon. Not all of us, not even most of us individually. Most people, most of the time, are reasonably content to live within the boundaries of the known. But as a collective, as a species, we have never, not once in the entire documented history of our kind, encountered a boundary and collectively decided to stop. We have always eventually gone past it. The first modern humans who crossed the land bridge from Asia into the Americas were not sent by a mission control. They were not responding to a funding opportunity or executing a strategic plan. They were doing what our kind does, moving toward the unknown because the unknown was there. The Polynesian navigators who crossed thousands of kilometers of open Pacific Ocean in outrigger canoes, using the stars and the currents and the behavior of birds to navigate between islands too small to see until you were almost upon them. They were not doing it because risk management demanded it. They were doing it because something in the human spirit finds the edge of the known world, not as a warning but as an invitation. Every generation has had its version of the horizon, the mountain range beyond the valley, the ocean beyond the coast, the continent beyond the ocean, the atmosphere beyond the continent, the orbit beyond the atmosphere, the moon beyond the orbit. Mars is the next horizon, not the last one. There is no last one, as long as our species persists, but the next one, the one that our generation gets to reach toward. And here is where the science and the poetry converge in a way that I find genuinely astonishing. You are made of atoms that were forged in the cores of stars that died before our solar system existed. That is not a metaphor. It is not a poetic flourish. It is a precise, scientifically accurate description of your physical composition. The carbon in your cells, the oxygen in your blood, the calcium in the bones that Mars would slowly dissolve. Every heavy element in your body, heavier than hydrogen and helium, was produced by nuclear fusion in the interior of a star, or in the cataclysmic explosion of a star at the end of its life. You are, in the most literal possible sense, made of stardust. The universe made matter, and matter made stars, and stars made the elements, and the elements made you. And now you, This temporary, fragile, improbable arrangement of stellar debris are contemplating returning some of those atoms to space, standing on a planet that those atoms have never touched, looking up at a sky that those atoms have never seen, carrying inside your skull 100 billion neurons that those atoms assembled into something capable of understanding where they came from. The universe made something that can look back at itself and wonder. And that thing is now asking whether it can extend its reach to another world. There is something in that story that I find almost impossible to hold in my mind without feeling the full weight of it. Not the danger, not the logistics. The sheer audacity of the fact that we exist at all, and that existing wasn't enough for us, and that the same restlessness that drove our ancestors across oceans and over mountain ranges is now pointing at the red dot in the night sky and saying, "There, but let me bring it back to you," specifically, personally, because this entire journey, all 10 parts of it, has been framed as a second-person story. You on Mars, your body losing bone density, your immune system struggling, your mind processing the silence and the distance, and the weight of being unreachable. And I want to be honest about what that framing means. You probably will not go to Mars. Statistically, almost certainly not. The first crewed Mars missions, when they fly, will carry a small handful of people, perhaps 4, perhaps 6, selected from a candidate pool of the most physically capable, psychologically resilient, technically skilled human beings on Earth, filtered through years of training and medical evaluation and mission-specific preparation. The odds of any individual person being in that group are extraordinarily small. But here is what is also true. The reason those people will go, the reason the missions will be funded, the technology developed, the decades of preparation completed, is because our species, collectively, decided that it mattered, not just the engineers and the scientists and the astronauts, all of us. The people who watched the moon landings and felt something move in them that they couldn't fully name. The children who looked up at the night sky and asked questions that their parents couldn't answer. The adults who followed the Perseverance rover's first drive on Martian soil and felt irrationally but genuinely proud, as if something they were part of had accomplished something real. You are part of the species that is going to Mars, not as a passenger, as the culture, the curiosity, the accumulated human insistence on understanding the universe that makes the mission possible and meaningful. The astronauts who stand on that surface will be standing there on behalf of all of us. Every person who ever looked up at the night sky and wanted to know more, every student who stayed up too late reading about planetary science, every parent who answered a child's question about stars with honesty instead of dismissal. The mission is not separate from you. You are part of what makes it real. So let's return to the title of this video one final time: why you wouldn't survive 1 year on Mars. The answer, in full, is this: your body would be relentlessly attacked by radiation that your planet has spent 4 billion years shielding you from. Your bones would thin and your muscles would shrink and your heart would lose capacity and your immune system would struggle in ways that our best current medicine can slow but not stop. The perchlorates in the soil would threaten your endocrine system every time the dust moved. The temperature swings would test your engineering to its limits every single day. The pressure outside your habitat walls would kill you in minutes without perfect equipment. The distance from every other human being not on your crew would create a kind of psychological isolation that no human in history has experienced. The cognitive costs would accumulate. The physical costs would accumulate. The mission would demand, continuously, more than your biology was designed to give. And despite all of that, despite every number, every risk, every documented consequence of what an alien planet does to a human body, people are training right now to go there. Engineers are designing the systems that will keep them alive. Scientists are running the research that will reduce the risks. Mission planners are working through the contingencies. And somewhere, a child who hasn't been born yet will grow up to be the first human being to stand on Martian soil, look up at the sky, see a small blue dot among the stars, and understand with every cell of their improbable, stardust-built body that they are part of something that started the moment the first human being looked up and wondered. We are not built for Mars, but we are built for this, for reaching, for wondering, for going anyway. And that, more than any engineering solution or medical countermeasure or mission architecture, is why we're going. And if you thought surviving 1 year on Mars sounded brutal, wait until you see what actually living there would look like. That video is on your screen right now. Click it. You're not going to want to miss it.